Get the door closed so the birds don't cause a disturbance. Alright, I'm going to bounce out of here so I can get to the live stream. So, if you're going to bed, I love you night. Hey everybody, welcome in. Hope the stream is going good. Hope your night's going good. So, yeah, tonight I'm just going to go back into the week one of, more or less speaking, what my college class was. We're kind of just covering the CompTIA Network Plus study guide. So I'm going to just go over the week one stuff starting at the very beginning of the study guide. And we'll utilize all the tools we have. We'll take notes on all of the acronyms that we're going to be exposed to. We'll utilize Cisco Packet Tracer to kind of play out some of the different aspects of a network. And then we'll also YouTube some stuff if we need some more clarification, because I'm not an expert, as the disclaimers very much so point out. So yeah, let's run through this together. I like to take things nice and slow. Speed is the enemy of retention. So we'll go through things nice and slow. We'll get our acronyms written down because, oh my goodness, it's so challenging getting into networking just because of all of the acronyms. I came up with the analogy of it's a lot like trying to learn biology. Like if you think about when you were in high school or whenever you may have taken biology, you have all of these new words to learn and new systems to learn about, and then how all of those things play a big, deeper role into like how a cell works and how different things work out within there. Like you have DNA. What is DNA? Deoxyribonucleic acid. And then like what part is DNA a part of? And then how does that play into the cell? So it can be challenging, but we'll take it nice and slow. I don't know how long we're going to do the live stream for. I'm gonna try to stay with it until maybe we just get all the way done with chapter 1. And maybe this is something we try to do once a week as a live stream over the chapters. I'm trying to set it out to where Monday evenings is Monday evening my time is when we get this stuff done on a consistent basis. We'll do the live stream, and then maybe I make a video to briefly summarize everything that I'm covering during the live stream. We'll see how this plays out. This is more so to help reinforce the lessons to me, as selfish as that sounds. And let's get to it. So I don't know a whole lot about the whole copyright thing associated with like trying to do teach back for like the CompTIA Network Plus. So as much as possible, I'm going to keep the study guide off of the screen. And then if I need to pull it up to just show you kind of like the diagram that they have, then we'll work that way. Let me find that study guide and bring it onto my screen. All right. So we'll go ahead and transition over to my desktop capture. I have 2 screens. I have my primary monitor, which I'm capturing for the live stream, and then I have my secondary monitor to set up OBS for the live stream, and that's where I'm going to keep the study guide as well. So let's just transition over to the desktop and see how that looks. Transition there. And then double check the stream just to make sure that's all looking good. Yeah, that's coming through nice and clear. Perfect. All right. So let me get that study guide pulled back up. All right. So chapter 1 is just an introduction into networks. It looks like the things we're going to be covering are like mesh topology, star, hub, and spoke, bus, ring, hybrid topologies. All right. So it's just kind of how we're laying our network out. And then network types and characteristics, we have peer-to-peer, client-server, local area networks, metropolitan area networks, wide area networks, wireless local area networks, and there's a whole plethora of the different categorizations of networks as well. So on the side here, I know the big things that we're working with. Since we're in now chapter 13 where I'm at in college, big things we need to hold on to are local area networks, LANs. So that's going to be our local area network. And if you are coming from a networking background and experience, this is going to be extremely slow paced because the way I teach is to like the lowest common denominator, running under the assumption that somebody has no computer experience or networking experience, because that's what I have. I've not come from an IT background. I just finished my prerequisites for my degree in cybersecurity, and now we're finally getting into the core material. So I'm going to go very slow and very easy with it. Let's see. The next thing that we've definitely used a lot through class is WAN, or wide area network. All right. We haven't really, WLAN, or wireless LAN. Ah. WLAN has been used where we're at now. we haven't really gone into too much of like the campus area network or storage area network or software defined wide area network. We have covered multi-protocol label switching. That's something we've talked about. And let's see, we have the multi-point generic routing encapsulation. We've talked about that, and we can put down more of these acronyms as we go through. Okay, then we have service-related entry points, which is demarcation point and a smart jack. We have visual network concepts like the vSwitch or the virtual network interface card, network function, virtualization, hypervision. Yeah, these all sound super complicated, but the study guide does take a good amount of time to explain all these things. I do think it fails in some parts of giving a in-depth explanation, so that way we can truly understand everything. So yeah, let's just go and we got past like the topics of conversation. Let's break into the actual material. Let's see. So first things first, as it says, what's a network? The dictionary defines a network as a group or system of interconnected people or things. And then it goes on to explain that when we're talking about IT or in the computer world, a network means two or more connected computers that can share resources such as data and applications, office machines, an interconnect connection, or some combination. And I've done a video on it, but just for fun, let's go into Cisco Packet Tracer, and I'll make that big for us so we can see it better. And let's just create the most basic of basic networks. So we'll go ahead and grab two computers. So here's computer 1, and then we'll grab computer 2. And that's all we need to know is we have two computers. And I've never succeeded at this, so let's see if I can embarrass myself on live stream in adding a printer. But let's just add a printer. Yeah, we have a printer we can share now. Let's see. All right, so we have our three nodes, if you would. A node is another way of identifying something on a network. That's a node. So we have three nodes. Let's give them names, right? So we're talking about IP addresses. So IP stands for Internet Protocol. Internet Protocol, IP. So we're going to go and this is also Cisco Packet Tracer. I didn't talk about that. So Cisco Packet Tracer is 100% free. You just have to go into their website and register and then start their courses. And then after you get through the introduction, at the end of the introduction, then they have the area where you can download Cisco Packet Tracer. And it is very, very useful, at least in regards to conceptualizing networking. Yeah, it's monster time. And I really dig this program. We've used it for a few labs in class. It's 100% free, and things are very interactable. So let me just give you guys a walkthrough. So down here, we have our network devices, our end devices, components. We have our wires, miscellaneous. I haven't played in here at all and haven't used this at all. Most of the time I'm playing in the network devices and end devices, and we have like routers, switches, hubs, wireless access points, security. I haven't touched this at all yet, so that's okay. It's okay. We're learning together. And as I go through the labs and learn a little bit more, I'll tell you guys about that as well. And then we have our emulations, which is like our connection to the internet. So we don't need to worry about that too much. So we're talking about at the most basic terms, what is a network? So we have three nodes or three devices for our little network. It's at least two computers that can share resources. So I don't even need the printer. So if there's like files on computer B down here and computer A wants to access those files, as long as they're able to talk to each other and share that information, that's technically a network. But for our example, we're going to use these 3 devices here. Well, we need a way of connecting all 3 devices. It's a little bit challenging just to round robin wire everything together because we only have one Ethernet port on the back of the computer, and you guys can see how dated these computers are. We got the floppy disk drive, we got the CD drive, like at least for work. I know we had to burn some CDs because I work in security and like we have video footage. We had to burn CDs and they had to order us a external CD-ROM, and then we put the CDs in there and burn the video footage to the CD. But like, yeah, even their computers didn't have CD-ROMs after we got them upgraded. So yeah, and yeah, you can change these out. You can change them to that's another Ethernet port, another Ethernet. So here we have a fiber port, and then you have your Wi-Fi ports. So it's just how we connect to the network or the internet, if you would. So let's take a gander at this. We want to connect all the stuff together. And I did a video on it in the past, but just as an analogy for you guys, think about like trying to communicate with a friend, right? When you want to talk to a friend, you typically want to know your friend's name. So we need to give our friends some names, and then we need a way of communicating with our friend. In real life, we have talking to them in person. In real life, we have calling them on our cell phone or text message. Computers are kind of the same way. We need a way of talking, which is our Wi-Fi, our Ethernet cables, or our fiber cables. So we have our computer here. So we're going to go into the desktop, and then we're going to go into IP configuration, and we're going to give our friend a name. So we have a way of statically assigning a name. So static assignment is where we have to physically go in and give them a name that does not change. So that's what a static assignment is. And then DHCP is Dynamic Host Control Protocol, if I recall correctly. Remember, I'm just in week 5 right now. Week 5 started today of class, so I might get some of the acronyms wrong, but we'll correct that as we go through. And what DHCP does is it dynamically assigns a name to the computer. Dynamically means like it does it on its own. It gives it its own unique name. We can set up different characteristics like, hey, I can change how long this computer has this IP address. And an IP address, just to make it very simple in terms, is the name of the computer. So we have a MAC address, which is Media Access Control. So MAC address is the burned in. They use that term a lot. It's the burned in address on the network interface card, I believe. So that's an address that doesn't really change at all unless you change out certain components. So think of that as like your last name. And then a IP address is kind of like your first name. You can kind of think of it like that if you want to segment it down. So we'll talk a little bit more about MAC address and IP addresses as we go on. But we're just going to think about it in terms of we're giving the computer a name. So we're going static. So that way we assign it ourselves. Now let me go back. IP configuration. So we're going to go static. And then let's just give it a name of 192.168.1.1. So the way an IP address is set up is each section between the dots is called an octet. Let me get my notepad back up here. Where are you at? So here we go. Let me grab this. So an IP address. And we're specifically talking about IPv4, which is Internet Protocol version 4. So we have the potential of having 3 numbers, which is like this. So 3 numbers in each octet. So we have a dot, we have a dot, we have a dot, we have a dot. So this section right here and this section right here, and this section right here, and this section right here. So these groups of 3 numbers, that is 1 octet. And an IPv4 address altogether is 4 octets. There we go. So an IPv4 address is 4 octets. So we'll just remember that, and we'll touch back on that in a little bit. But it's okay. Right now, let's just focus on where we're at in the lesson. Let me see if I can erase that all. Oh, that looks like doo-doo. Use the more advanced version. All right, we can get rid of the notepad for now. So we're just giving this a name of 192.168.1.1. And you're going to see a subnet mask in there. We'll talk about those later, but that's okay. Right now we're just focused on, we're giving this computer a name. So we're going to give this computer a name as well. So we'll go into desktop, IP configuration, and we'll go 192.168.1.2. All right. So both of our friends have a name now, and that's good. Now we need to give them a way to communicate, a way to hook them up together. And the way we're going to do this is we're going to go down here, and we're going to grab a hub. A hub is just a device that allows us to link a bunch of computers together. It's not a smart device. It doesn't really help do anything. All it does is it captures whatever data is being sent to it, and then it sends it off to everything else on our network segment. And we'll get into explaining a little bit more about a hub in a bit, but that's okay. Right now we have our 2 computers, and we have a hub, which is just a way of connecting the computers or our other devices like our printer. And now we need to go about wiring them up. So we're just going to grab an Ethernet cable, and we're going to put it into the fast Ethernet port on the back of the computer. And then we're going to go to our hub, and you can see that we have a bunch of Ethernet ports on the hub. We're going to plug it into one of the Ethernet ports there. Same thing with this computer. We're going to plug another Ethernet cable into it, and then we're going to also plug it into the hub. So our 2 computers have names now, and then we have a way of talking to each other via connection to the hub. And let me see if I can also connect my printer. Oh, looky there. Hey, we're all connected up now. So now we're also sharing a resource, like a printer. The example that they provided in the study guide kind of looks like this. I'll bring that in and show you. So they have host 1. So nodes and hosts. Host is kind of used in the sense of sending and receiving data, which they get into those definitions a little bit later. But you can see we have computer A hooked up to computer B. Computer B is hooked up to computer A and a printer. So that's kind of the example that they give. Considering we only have 1 Ethernet port on our second computer here, I thought it'd be easier to just connect it to the hub. So we want to see if computer A will talk to computer B. So we have a method of doing that in Cisco Packet Tracer. We can go up here to the add simple PDU. I forget what PDU stands for. I think it's something data unit. But we'll go ahead and grab that. We'll drop it into our first computer. And then to see if we have connection to the second computer, we'll click on that computer. And we can see that we're successful. We're successful in sending data from computer A to computer B. The neat thing with Cisco Packet Tracer is we can also do the simulation on it to see how this happens. So we'll hit play. We can see that the message goes to the hub. And then from the hub, it'll go to every device on the network. So you see it goes to the printer, and then it also goes to computer B. And then computer B is going to send a reply, which goes to the hub. The hub then sends it back to everybody on the network. And then computer A is like, good, I got the packet back. Or I got the response back that they received the packet. So another way of testing this is we can do what's called pinging. So we'll click on the computer, we'll go into command prompt, and then we're going to ping 192.168.1.2. We'll hit enter. If I typed it incorrectly, which I think I did. Oh, we're still in simulation mode. Let's go real time. I apologize. Okay, there we go. So pinging with 32 bytes of data, and we sent the data over. Packets sent was 4, received was 4, lost was 0. So we had good and successful communication with computer B. All right, so that's how they define a network. It's at least 2 computers that can share resources. At least 2 computers that can share resources. That's what a network is. So let's read through here and see if I may be missing anything. Yep. All right. So the 2 hosts talk to each other. Perfect. Next, I'm going to tell you about local area networks and how they work. Perfect. So the big thing with local area network, and like all of the other types of networks that we've covered, like LANs, local area network, WAN or WAN, wide area network, wireless LAN, WLAN, is it's kind of dependent on the way data is moved and then how big of an area we're talking about, and then in addition to that, what type of area are we talking about? Because we saw something like the campus area network. And if you think about a college, right, you might have like the science department, and then science department's broken down into, you have the geology department, the physics department, the chemistry department. Like everybody's going to have their own local area network, but they all can kind of connect to each other. And that would be like the campus area network. And it's a campus because it's a college campus. So let's see. They go on to explain that back in the day, you couldn't put more than 30 workstations on a LAN because there was a limitation to how far the machines could actually be from each other. But we have technology advancement. Let's see. Yeah, they go into also showing us like network segments. So we can do that. We can go over a network segment. So that's exactly what we've created here. In essence, we've created a network segment. This classifies as a network, but it's also a network segment as well. So let's get this a little bit more organized. So we have our network segment over here, and if we wanted, we could add some more stuff. That's okay. And then let's get another network segment set up. So we'll go into switches. We'll just grab a switch and bring that over here. And let's grab some more devices. So we'll grab and devices and get over here and get some PCs. So we have some PCs. What else might we want? We'll just keep it simple today. We'll just keep it simple. Let's wire these up real quick. And a switch is a little bit different because a switch is a little bit smarter. And we'll cover switches here in a little bit. And I'll just follow along as much as I can with the study guide, so that way we don't get too repetitive here. So we have our 3 computers all linked up. We can go into desktop, IP configuration. We can also give them names. And we'll get a default subnet mask. That's okay. We'll cover those in a little bit. I don't think it's in chapter 1, but we'll get there. IP configuration. All right. So we can do another test here. We have our three friends. We have a way of talking. This time we have a switch. A switch kind of works in the same way. If we go and we look at it, you can see we have a bunch of ports in the back of the switch. And a switch is just a little bit smarter because it actually assesses the MAC address of the data. And if it recognizes that MAC address on its segment, like if we have computer right here, which is 192.168.1.3, wants to send something to 192.168.1.5, that's this computer. When it sends it to the switch will look at that and be like, oh, I know where that's at. It's on this port. It's on this plug in the back. So if we look at it, we have all of these ports. It knows which port is what. It knows. It has their own interface. As we click on, well, we can just hover over this right now. Actually, I got a better way. Delete. No, I don't want to delete the switch. Let me hit the delete button. There we go. And let's rewire that, and I'll show you. We'll go back to that, click. So we see we have the interface fast Ethernet 0. And then when we click on this, we have all of these different ports, right? And they're all labeled. They're all labeled. And the switch knows which port is what. It's smart. So it knows which port. So it will know that whatever the MAC address for computer B is going to be on interface number 2. As soon as data goes out to the switch from one of those devices, the switch will recognize like, oh, this MAC address belongs on this port. And the Ethernet plugs in the back, those slots, that's what's known as a port. So a switch is smart. It'll figure out and determine what computer's on which port. And every once in a while, the switch deletes that data and then it reassesses like, hey, I just want to make sure that this device is still here. Hey, device, what are you? It'll refresh that information. So anyways, a switch is slightly smarter, and we can test to see to make sure that our friends talk to each other. We have our friends. They've been given names, and we have a way of them talking. We can go grab a packet, put it on computer A, and let's test computer B. And we see that we're successful there. And remember, when we did it with the hub, when I wanted to send data from computer A to computer B, and it went to the hub, it went to every other device on that network segment. So let's do the simulation. Oh, sweet. We still have our first packet from here. So we can see these both happen in real time. You can see the difference. So the data goes to the device. And that didn't work out quite what I thought it would. Wonder why that is. Maybe because it doesn't know who is who yet? Still learning as we go, so let's see what happens. Okay. I noticed that the return, or was that the return? Let's see. Let's try another piece of data. See if maybe we learned who is who yet. Hey, now we know. So it waits on the data to go from the computers so that way it can learn and figure out who is who. Allegedly, this will just go to this guy. We'll see. Yeah. There we go. They have to learn first. All right. Like I said, I'm going to make mistakes because I'm learning as we go. And this is live. It's all good. So let's recap real quick on a switch. So a switch has to learn first who is who. In order for it to learn first, it has to receive data from that computer, like, hey, this is my name. So that's why, initially speaking, we had a broadcast where it went to everybody on the network segment. It learned everybody's name when it got replies, and then from there, it distributed things as it should have. All right. Let's go ahead and end the simulation. Okay, so we have our two network segments. We have segment A, and then we have segment B. And let's see, what's it wanting to get into here after this? Yeah, it also emphasizes don't stress about devices such as hubs and switches. These are just connectivity devices, and we'll cover those later. Let's see. And we have these two segments, right? And we might want them to talk together, and that's where we're going to get a router. So let's go to our network devices, and we'll grab a router. All right. So a router, what we're able to do then is if we have different networks or different network segments, we then have the ability to forward traffic. So let's just say this was a different network. You know how I assign the IP addresses? Well, the IP addresses can be different depending on the network, and we'll cover that later. But a router can forward traffic from network segment A to network segment B, or from network A to network B. Right now, we're just going to focus on creating a local area network. So we'll plug into the hub. Did I grab the wrong cable? I did. And then we'll plug into the router. And then we'll grab a plug. And then into the router. Cool. Now, allegedly, once we configure our router, everything will be able to talk to each other, and we've created a local area network, if you would. And there can definitely be more devices over here. So like, let's just say this is like our sales team. You can also have servers here as well. So maybe I'm storing client data in here, and the sales team might want to connect to that server. And then let's just say this is, I don't know, customer complaints. Like they work in a different part of the office, but they might need to get to the server to also get some client data. We can connect the server to the hub as well. And boom, bada bing. Let's see. Let's work on it. And let me show you what they were talking about in the CompTIA study guide. So we have our two network segments. So we have marketing, then we have sales. And like I said, he says don't stress. And then a little bit further along, we link it together. It goes over just basically some problems. Notice that marketing and sales work group are LANs in their basic form. Any device that connects to marketing LAN can access the resources in the marketing LAN. And LAN, once again, is local area network. And he also goes to call the network segments work groups as well, because you can have like marketing and then sales, and they can be like different work groups. Where did that go? That's not it. I minimize you, now I can't find you. That's not it. I'm going to close Discord. I'm not in there actively. Oh, let me find that. So go into my CompTIA folder, chapter 1, get you back up. PDF isn't showing at the bottom of my manager either. All right. So we'll get that back over. I'm not super familiar with copywriting yet, so I don't want to get struck down. Let's see. So problem solved. We can use the routers far more than just connecting LANs. The router shown is a great solution because the host computers from sales LAN can get to the resources in the server and printer. So if we had, we have our server and printer here. So if this was marketing and this was sales, somebody from marketing can access the server, somebody can access the printer, and that's good to go. So let's see. The next section, so that covered, if we scroll up, that covered local area network, right? Which is a place of specific geographic, restriction. And the thing is that's challenging is like they don't really specify how big a LAN is. It's just kind of local to the area, if that makes sense. So he says, because this is written by Todd Lamon, he says, just as the name implies, a local area network is usually restricted to spanning a particular geographic location, such as an office building, a single department within a corporate office, or even a home office. So, I mean, technically, my office setup right here could be considered a local area network. If we were to set my network up in real life, let's delete this stuff. Let's just do that for fun. So right now I'm working on my PC, right? So I have my PC. So no, I don't want to delete you. I want to rename you. So we're going to do my main PC. And then, I have a little Mac Mini that's also set up to my computer via a HDMI cable, and I can capture that in OBS. So we'll do my Mac Mini. And that's just sitting on my desk. Let's see, what else do I have? I have all of my networking components here. Let me see if my OBS is capturing that. Let's switch to my big camera. Thank you, Tanapon Tomangi Wong 8049. So if we transition to my my big camera, let me get the camera to lock in place here if it wants to cooperate. I have the Insta360 link. Sometimes the AI likes to cooperate, sometimes it doesn't. Yeah, here's my headset stand. Don't mind that. Let me move that out of the way. All right, let me see if I can't adjust the camera a little bit. All right, there we go. So we have my modem, which stands for modulation, demodulation. What it does is it takes the coaxial cable from my internet service provider and it turns it into a digital signal. So that way all of my computer equipment can recognize it. And even if you have fiber, you have to have a modem. You need to be able to turn those light impulses into digital signal, or you turn electrical energy into digital signal. So that's what your modem does. And most of the time, and let me grab it. Most of the time people have like the 3-in-1 Wi-Fi modem switch combination. Like you can see how it's a switch. Like we have our different Ethernet ports on the back. So it'll determine when you plug stuff in, like your computer, your Mac Mini, so on and so forth, like where data should go. When do we forward this off to the internet? When do we forward it off to other devices on the network? And then you can see where the coaxial cable plugs in. So this is like an all-in-one thing. But after I started this class, I was like, oh, let's get equipment so we can practice. So let's go back to my equipment. So we have the modem, and then this is a router, and it also works as a switch. And we can see that I have a bunch of different stuff plugged in. So this comes from the modem, and it plugs into the router switch. So that gives us internet access. Then we have my PC that's hooked up. We have my Mac Mini that's hooked up. And then this Ethernet cable, I'm sorry, no, this is the Mac Mini. This is my PC. What do you hook up to? Oh, this hooks up to my wireless access point. So it runs all of my Wi-Fi. This is a random cable I have going out to my living room for when I want to game out there on my laptop. And then this hooks up to the Mac Mini. So it switches the data coming from each device if it needs to go onto other devices on my network, or it forwards the traffic to my modem, which then goes to the routers for the internet service provider that can go out to the different routers on, the different websites, right? So that's my basic home setup. So let's try to emulate that in Cisco Packet Tracer. We'll go back to the desktop. All right, so we got my main PC, we got my Mac Mini, and then essentially speaking, we have my switch, which is also my router, but we'll just segment this out into different devices. And then we have the router as well. And then we have my wireless access point. It's all kind of stuffed in my bedroom. That's where I'm running everything. And then we'll just hypothetically go with the wide area network emulation tool. Like this is my modem. It goes to the internet after that. And then what else do I have? What else do I have? So end devices. Let's see. I have a TV in my bedroom. And then I have a TV in my living room. I have a laptop in my living room. I have a laptop in my kitchen, which is in my go bag. Like I use that for like studying on the fly, like if I'm going out to study. Let's see. What else do I have? And then I have my cell phone. So we'll just throw that somewhere. Yeah, I have a cell phone that most definitely doesn't have an antenna sticking out of it. Let's see. I have a tablet that's also in my bag. We can throw out another tablet in my room because I'll count my Remarkable Paper Pro as a tablet. We'll just put that over here. All right. So that's basically my, local area network for my house, if you would. And then, yeah, you would go about linking everything up, and then the wireless access point would connect to all the Wi-Fi devices. But yeah, that's essentially how it's broken up, just for fun. All right, let's go back to the study guide if I didn't lose it. All right, we got the study guide. Make sure OBS is good. OBS is good. All right. So we covered local area networks. We covered the basis of what a network is. Let's scroll down a little bit. So we talked about connecting work groups or network segments together. We talked a little bit briefly about a router, nothing in detail. Yeah, he talks about we could just have taken a wire and attached it to the hub of one work group and then attached it to the switch of the other work group. The problem is you just have one big cumbersome network right there. Routers are really good in the sense of they can break up networks, which they get into some detail later. So not going to go into too much detail. We're just trying to go with chapter 1 for now, because if somebody's trying to go through the CompTIA Network Plus study guide and study materials, if we do it bit by bit, I think that's fine. And then we can get into more details later. So common network concepts, we have workstations, servers, and hosts. So I did do some research on this because I was like, all right, so a workstation is a computer, right? And then we have computers. But the big difference is workstations are mega powerful. And I found a very interesting YouTube video that went on to have a guy explain kind of the difference. Because like workstations can have like multiple CPUs in them. And they can have multiple graphics cards in them. Like they're big and beefy. And yeah, he explains that. He's like, workstations are seriously powerful computers that run more than one central processing unit or CPU, and whose resources are available to other users on the network to access when needed. So like an interesting thing about a workstation is like it is a seriously beefy computer with a lot of processing power. a lot of RAM. It's almost like a server, but servers are very specific in what they do. And we'll talk about servers next actually. But like workstations are big, thick computers, and you're kind of running applications on them. For example, if you're making anime, like as a good example, and you need a big beefy computer to run um, the video editing on, or adding like audio to it, things of that nature, or if you're making a video game, like you need a big beefy computer to do those things, and you can basically connect to a workstation and have it do all of the hard work while your PC is like doing some work to connect to the workstation, but the workstation is really putting in the work for you. And you can have multiple people connected to the workstation. Like, let's just say we had a team of 5 people working on a section of an anime. We're doing a fight scene for solo leveling. And we're all working off of this workstation to try to make the scene. I don't know if that's quite a good description, but at least as far as I've come to understand it thus far. He goes on to explain, like, with that much power, you might think that he's describing a server, but it's not quite. The difference is workstations are often employed as systems that users use on a daily basis. So like I said, yeah, like video editing or game creation. Yeah, and then he goes into client and host, essentially speaking. Those are kind of roles that anything takes on, which they'll cover in a little bit. But a workstation is like a super beefed up computer. And yeah, let me see if I can't find that YouTube video, and I'll at least bring it up to show you guys. Yeah. Here, let me get my caps lock off. I'm not going to watch the whole video. I'll just pause it and show you guys. So essentially speaking, like this is like a higher end gaming PC. And gaming PCs are kind of designed to let's do things quickly and fast because you want like higher frames per second and things of that nature. Whereas workstations are kind of set up to let's do a lot of things at once, kind of fast. And let's see, what did he have to say about this? He kind of went on to explain a little bit, but this video is titled Workstations versus Desktops, What is the Difference? And yeah, that is by Media Man Studio Services. Very interesting if you want a more in-depth explanation on workstation versus like a regular computer. And like I said, they have like multiple graphics processing units, a lot more RAM, a lot more storage. Like you're talking the magnitude of multiple terabytes of storage. Whereas like with regular gaming PCs, like you're doing pretty good at a terabyte or up to like 5 terabytes. Those things are like 5+ terabytes of storage, and then like a ridiculous amount of RAM comparatively. Let's see. So that's a workstation. So just a super powerful computer. Let's see. The term workstation, client, and host can sometimes be used interchangeably. Computers have become more and more powerful as the terms have become somewhat fuzzy. So servers. So servers are also very, very powerful computers, as he says. And there's a multitude of different types of servers. They're kind of very specific in like their role and their functions. Let's see. Let's find a picture of a server. That way we can just pop that up on the screen. Images. So yeah, let's just pop this up real quick and I'll show you guys. So servers, they're not pretty at all. They're kind of focused on a lot of power, having a lot of redundant systems in place. So if there's like a power loss or a power supply dies, um, they're set up to where they can, you know, overcompensate for those losses. And then they have like a bunch of drives on them for storing data. And then they have redundant drives as backups to store data just in case one of the drives dies. So they're very modular in that like replacing equipment in them is a little bit easier. They're set up for very efficient work, and they're very job specific. So like, yeah, these are like server rooms that you can see. And yeah, these rooms are super, super cold on the inside. Like you have a hot side and you have a cold side where cold air is coming in and it's pulled in through the fans of the server, and then hot air comes out the other side, and then you have exhaust to capture that hot air and send it somewhere else. So they have to keep these rooms super cold. But yeah, I was also watching Network Chuck, and I guess you can go on eBay and Amazon and buy servers yourself and then like set them up. But there's a multitude of different types of servers. Like you'll have servers that are for sharing files. And another cool thing about servers is like multiple people can come in and access the servers. They're definitely designed for high traffic going through them. Whereas if a lot of people were trying to, if I was running my desktop PC as a server, which you can do, if a lot of people were trying to access that, it just doesn't have like the computing power to deal with that. So you want something that's very specifically designed to have a lot of people come in, and you want to have security in place to make sure that the people coming in can't mess with stuff. And they serve very specific functions like sharing files. Then you have email servers. So think about like your Gmail, right? We have very specific servers set in place for that. So print servers, a server that, you know, will receive stuff to send out to the different printers. Web servers, very, very good example. Like if you think about how many people are using google.com, you want very specific servers for loading those pages. Fax server, I don't think people are using fax too much anymore. Application servers. So yeah, if I'm running like a phone app, for example, like US Bank, if I were loading in to check out my banking information, we'll have servers for that. Telephone servers, yeah, like call centers will need that. Proxy servers. So a proxy server is just kind of like, here, I'll show you on here. So essentially speaking, let's get our PCs all lined up. So we have our PCs, and then we'll have some servers in the back. Let me find the servers. So let's just imagine we have this all linked up together, and we have our networking devices in here. So we have our switch, and then we'll have a router, right? So if somebody from the internet was to come in, it'd go through our router, then into our switch, and then from the switch to a multitude of different things are potentially available to us, right? So we might not want that. We might want something in place in front of this, so that way somebody doesn't have direct access or direct linking to our servers or our workstations. So they create what's called a proxy server, which is, let me grab another server in front of here. So essentially speaking, when somebody, here's my computer. And when I want to access information, I talk to the server like, hey, server, which is something my company trusts. I trust the server. Hey, server, I want this information. Then the server itself goes and collects that information, which is something I trust. And then it sends the information to the client, whoever wants that. All right, so that's a good example of a proxy server. Let's see. So as he says, quote, servers are usually dedicated to doing one specific important thing within a network. Not always, though. Sometimes they have more than one job, but whether servers are designed for one job or are network multitaskers, they can maintain the network's data integrity by backing up the network software and providing redundant hardware for fault tolerance. And no matter what, they all serve a number of client machines. So that's where he kind of breaks down as to like what a server and a client is. I mean, it's super funny. I didn't think about this until later. But let me transition over. I didn't think about this until later, but like I didn't use like the whole restaurant analogy of like server and client the entire time. Like that just wasn't in my mind. Like if you think about it in terms of a restaurant, like a client is asking for something, right? Like I go to a restaurant as a customer. I'm a client. Like I want the matcha. And then the server goes and serves me the matcha. Matcha would be like, I want this data. And then the server collects, gathers, and presents the data to me. Like, yeah. I mean, it's probably a bad analogy, but I never thought of that before. So let's get back over to our study guide. Hopefully I didn't lose it. All right. So yeah, we went over the figure. I want to make sure you know that servers have considerably superior CPUs, hard drive space. Yeah, they're very robust and mission built computers with tons of data storage and lots of CPUs, because you need all of that computing power when you have anywhere between 100 to thousands of people accessing something at once. Like you can imagine how many servers Google has to have. Like it's insane. Or YouTube. YouTube is a great example. Hey, that's where we're at right now. YouTube's a great example. Think about how many servers they have to store all of the data from all of the videos. Like, oh, let's Google that real quick. I remember that being like a pretty astounding number regards to like how much data YouTube has to store on a daily basis. We'll Google that. How much data does YouTube store per day? So YouTube stores an estimated 720,000 to over 1 million hours of new video content daily, amounting to several petabytes of new storage required every day, with over 500 hours of video upload every minute. Wow. So, yeah, imagine the constant need to having to like constantly upgrade your servers over time to make sure you have enough storage capability to hold on to all that data. It's pretty insane. All right, let's go back to the study guide. Should always put your servers in secured area. Yeah, that's cool. All right. So hosts. We're talking about hosts the next time. And I'll show you guys the figure that they use here. And we're about to get into hosts, but he was just going over servers here. And they're talking about like, this is like a network backbone, because you can see that a lot of data is going to be traveling over this right here. So we have all of our different work groups. We have sales, we have outside hosts potentially. And hosts want to access the servers as well. So hosts, let's get this back over here so that way I'm not copyrighted. So hosts can be, people refer to hosts as typically any type of networking device, including workstations and servers. But if you dig deeper, you usually find the term comes up when people are talking about resources and jobs. that have to do with TCP/IP, which is Transmission Control Protocol, Internet Protocol, which we'll get into that probably way later, because TCP/IP is covered in Chapter 6. So we'll just forego that knowledge, but depending on like the way in which data is traveling, your role changes, because every machine can be a client or a host. And hosts, if you can think about it, are kind of like sending data. Clients receive data. So my phone, for example, if my lady sends me a picture or a video message or a text message, at one point my phone is the client and it's receiving data, and at one point her phone is the host and it's sending data. And the role can switch when I'm sending her a text message, a video, or a voice clip, and I become the host and she becomes the client. So roles can switch a little bit, like depending on what's happening. But he goes into explaining that there's a bit of a background with it. And the guy who writes the study guide is super amusing. But he goes on to explain that back in the time, we had networking devices known as mainframes. Mainframes were the only intelligent devices on a network. And they were called hosts, whether or not they had TCP/IP functionality. And then everything else on a network was referred to as a terminal. Only mainframes were hosts because they had an IP address. And then back then we had the term gateways, which was used to talk about any layer 3 machines like routers. Let's see. All right. So after this, so we talked briefly about hosts. It's kind of a role. Client is kind of a role. Servers are kind of like purpose-built machines. All right. And then they go into explaining the different types of network classification. And I'll go back to the big screen because we're not using Cisco Packet Tracer too much right now. Go to OBS. On big camera. Sorry, everybody has to see me. So Metropolitan Area Network, or MAN. So that's one of the things we can write down that we may need to know about as an acronym. We can just write that down. MAN. And let's see. Let's go back to OBS. We'll actually just get my desktop going again, so that way my notes are up, because I think notes are more important than seeing me. Transition over here, get my notes up. So that'll be our Metropolitan Area Network. So that's our MAN, our Metropolitan Area Network. So Metropolitan Area Network. Did I spell that wrong? I think I did. Politan. Metropolitan Area Network is just as it sounds, a network covering a metropolitan area. So a metropolitan area network is, more or less speaking, a concentrated wide area network. Metropolitan area networks typically offer high-speed internet connections using ground fiber. Okay, wide area networks. So this is one of the bigger ones that we have to cover, or WAN. Wide area network, or WAN. Wide area network, or WAN. So one of the biggest WANs of all is the internet, and you use that every day. They span large geographical areas. They're typically worldwide, um, like the internet. WANs usually employ both routers and public links, and he goes on to explain that's generally the criteria used to define them. So let's break into his breakdown of it. Here's a list of some of the important ways WANs differ from LANs. WANs usually need a router port or ports. WANs span a large geographic area and or can link disparate locations. WANs are usually slower because you have so much geographic radius to cover, and you have a lot of routers, so you have a lot of time in between when information goes from point A to your switch to your router out to your internet service provider, maybe hitting several routers on the way there. And from your internet service provider, they have routers with big routing tables that determine, okay, how do I get to where you are trying to access? And then from there, you hit more routers until you finally get to your place. It does the application process of getting whatever data you want, and then it has to hit all of those routers, your ISP to routers, back to your home router to your network. And then you have a lot of traffic on those routers as well, because everybody on the world is trying to access them. So yeah, another big thing is people can choose when and how long to connect to a WAN, a wide area network. A LAN is kind of an all or nothing type thing. So if you imagine that you're at work and your PC is connected to the Ethernet cable, like if you were to unplug from there, you're no longer connected to the local area network. You can't connect to your printers or anything like that. So a LAN is all or nothing. Um, Workstations are connected either permanently or not at all. Um, and most of us now have dedicated WAN links. WANs can utilize either private or public data transport media, such as phone lines. Let's see. Okay, so here's another interesting tidbit. So we get the word internet from the term internetwork. An internetwork is a type of LAN and or WAN that connects a bunch of networks or intranets. In an internetwork, hosts still use hardware addresses to communicate with other hosts on the LAN. However, they use logical addresses, IP addresses, to communicate with hosts on a different LAN, which would be on the other side of a router. So yeah, let's go through Cisco Packet Tracer and show you what that means. All right, let me get rid of this real quick, and let's create a smaller network that's easy for us to manage. So we'll get some PCs. And then we'll grab a switch. So we'll go to network devices, and then we'll grab a switch. Remember, our switch is a smarter device. So the OSI, which is the Open Systems Interconnect, OSI model kind of is a multi-layer model that kind of shows how data moves from like application layer all the way down to like the physical layer, which is like how the ones and zeros are electronically transmitted. So switches, this isn't really super big to remember right now, but they're essentially speaking a layer 2 device. Switches look at the hardware address. So hardware, MAC address. And then we have IP address, logical address. So remember, hardware address, MAC address, and that's the burned in address on the network interface card. And we'll do a refresh on that. So the network interface card right here. All right. This device right here that connects to our computer that has the Ethernet port. That's the network interface card, also known as a NIC right here, network interface card. All right. We can change that out, right? We can change that out. We can get a Wi-Fi antenna. That's fine. Our network interface card is changing. Our MAC address changes. Or we can get a fiber connection right here. Once again, network interface card. That's okay. That is the hardware address, the MAC address, media access control, MAC address. All right. So we have our computers here. And when we're connected to the switch, let's just connect those real quick to the Ethernet port. And then we see we have all of these Ethernet ports. So we're going to go in to interface 1 and then Ethernet port. And then we're going to go into interface 2, Ethernet port, and then interface 3. All right. So let's see. Desktop. IP configuration. Let's just give this 192.168.1.1. And we'll go to desktop IP address 192.168.1.2. And then desktop IP configuration 192.168.1.3. Perfect. We're all set up now. So I assigned an IP address, which is the logical address. Okay. IP address, logical address. IP stands for Internet Protocol. IP is Internet Protocol. They are the logical address. All right. So we assign the logical addresses. However, what a switch looks at is not the IP address. It is not the IP address. A switch is a layer 2 device that looks at the MAC address, media access control address, hardware address. So once data has been sent to the switch, it will, for a little bit, remember who is on which port. Remember, the ports are the Ethernet plugs in the back. And the ports are assigned a number. The switch knows where the ports are. And it waits until it gets data from a client or any node connected to it. And once it receives data from there, it remembers who sends it. Because every time we send data, the client will provide a source address, which is its MAC address, which I wonder if it's, yeah, we can see here. If you look over to the right of this white box, if I move it, the problem is, actually, we can do print screen. Where's my print screen button? Let's see. Where are you hiding? Oh, no, it disappeared. So we'll do snip. That didn't work. We'll do snip. All right. Let me get this over here. I don't know how we're going to work this out. Let's just find the print screen button. Which one are you? Is this it? I think that's it. Hey, found it. Where'd you go? Boom. Yes. Okay. So now we got this here. So if we're looking at this computer, see the MAC address right here. Let's zoom in on that. Let's get that over here. Oh no, I don't want you. Update now. No, I meant later. Uh-oh, SpaghettiOs. Did I break my computer? Okay. Go away. Let's try that again. I am not the most computer savvy person. I'm trying my best here. Bear with me. Where to go? You want to give me? Ah, there we go. Sweet. So this computer that we just made, you see how it has the MAC address with 3 octets right here. So that's its hardware address. The hardware address. All right, and that's for the network interface card. So we got our IP address, which you saw me make. And then that's the logical address. Logical address. And then we have MAC address. That's a hardware address of the computer in Cisco Packet Tracer. Let's get rid of you. So when these devices talk through the switch, they're talking through the hardware or MAC address. MAC is Media Access Control Address. All right. So when we send data, we have a source address. The source is who it comes from. And then we have a destination address, who it's going to. So that's what our switch looks at and determines who to send it to based on that information. Okay? And that's typically within your network segment. Now, when we're talking about different networks, so like this network will be around the range of, let's see, let's get a note here. So we have 192.168.1.x, right? Because I've labeled the devices as 1.1.2.3, right? If we remember that. But we might have a different network over here. And this might be 192.168.2.x. That makes it in a different network. All right, it's a different network ID. And we'll get into those in later lessons. But I digress. Let's go back and see where I was. I had a point here. Okay, so yes, if we wanted to talk from this network to a separate network, a different network over here, like if we imagine we have our computers. Hey, we're doing this for fun. Why not set it up? Let's set it up. All right. And network devices, we'll grab a hub, the dumb hub. All right. And we'll connect these up. And I promise I'll get better at this. Let's see. Okay. Every once in a while I have to double check OBS because I've done it where I'm trying to like film videos and like I'll be partway into like talking. I've been talking for like 5 or 6 minutes and I'm demonstrating on Cisco Packet Tracer what I'm trying to do. And then I just happen to glance at OBS and I'm like, oh, I'm recording big camera of me. I'm not capturing my desktop. I still have to learn how to be a YouTuber. Which, you know, I'm not looking to do YouTube as a way of making money. Like, I look at it as two things I'm looking to accomplish. And since I'm kind of digressing over here, I'll switch back to me. There's 2 reasons I'm doing YouTube. One is that when I teach back and I feel confident enough in the material to where I can teach it back and talk about it, then I really reinforce in myself that I have proper understanding. And then 2, if there's anybody out there who wants to go slow and steady to make sure that we're grasping all of the information as we're going along, then if I can help them out, awesome. If I make getting into computers and IT easier for somebody else and give them confidence and help teach them, that makes me happy. Like, I love the idea. Anyways, that was our distraction. Let's go back. So if we want to talk to the network over here from a different network over here, we need a router. Because when we're talking to all of our buddies on this side, we use the MAC addresses, the source MAC and the destination MAC. All right. That's how we're going to talk to our friends. That's what the switch looks at. However, when we're wanting to talk over here to a different network, different IP addresses, different network. We need a router, because a router, let me grab a router. I think that's the right one. So many different routers. A router is going to receive that, and it's going to assess the IP address. That's what a router looks at. It looks at the IP address, Internet Protocol address. And it checks the Internet Protocol address, and then it figures out, where do I need to send this? All right, where is this network? And it does that with its routing tables, which it makes. And that's for way later in networking. So a switch will look at the MAC address, media access control address, hardware address. A router looks at the IP address, all right, logical address, Internet Protocol address. The hub is dumb. It doesn't look at anything. It doesn't look at anything. It receives and then sends it out to everybody. Everybody. A switch will learn. A switch will learn. So if I want to send a packet on a switch, it'll go from A to the switch, and then the first time it'll send it out to everybody until it learns the MAC addresses. It'll get the replies, because remember, everything has a source and destination address. It'll get the replies, and it'll remember who is where, who is on what port. And then going forward, it'll just send it to the recipient. Okay? But a hub does not. A hub does not. A hub receives and sends it out to everybody. So we want to go from network A to network B. We need a router. A router looks at the IP or the logical address. Okay, let's go back to our study guide. So we get the term internet from, we get the word internet from the term internetwork. Internetwork. An internetwork is a type of LAN and or WAN, local area network, and or wide area network that connects a bunch of networks or intranets. So this is a intranet. This is a intranet. This is a network segment. This is a network segment. This is a work group. This is a work group. There's a bunch of different names. I would refer to this as a work group when I'm referring to the sales work group. I'd refer to this as a network as a sales network. So, or the sales intranet. So it's kind of inside of its own thing. Intra is inside. I believe I'm getting that right. So in an internetwork, hosts still use hardware addresses to communicate with other hosts on the LAN. So this is an internetwork. It's going to use the hardware addresses. This is an internetwork. It's going to use the hardware addresses. If we want to talk from here to here, it's going to use the IP addresses. Okay. So routers are what's needed for this to talk to this if they're different networks with different IP addresses. Okay. The internet is a prime example of what's known as a distributed wide area network. An internetwork that is made up of a lot of interconnected computers located in a lot of different places. There's another kind of WAN, wide area network, referred to as centralized, that's composed of a main centrally located computer or location that remote computers and devices connect to. Good example is remote offices that connect to a main corporate office. So yeah, we'll go and we'll show what that looks like. Okay, let's get it. Yes, we want to delete. So let's say, what's a good place to go? What's a good place to think about this? Instead of just being vague, let's make it fun. So let's say we have, let's say we have Best Buy. Best Buy 1 or 2 words? How embarrassing. I think it's 2. I haven't been to Best Buy in a little bit. That's 2 words. Sweet. So we have Best Buy. And we'll say, click on you. We'll say Best Buy in Columbus, Ohio. And then we have Best Buy in, what's a fun place? Seattle. And we'll just say that these are different branches of Best Buy. And then we'll have corporate Best Buy. Let's Google that. Where's corporate? Where's Best Buy corporate? It's in Minneapolis. So let's see. We have Best Buy HQ in Minneapolis. So all right. So let's check this out. So when I go into Best Buy, right, they always ask for my email because it has my account information. And then let's see, what else might they store? And then they're going to have different storage for like all of their inventory, things of that nature. So we're going to have servers. 1 second, hydration break. So we have our corporate headquarters. We'll get our big beefy servers all set up. That's where we want to store all the goodies. And just for the sake of not putting in thousands of these, I'm just gonna do 4. All right, so we got our corporate servers. Let's connect those to a switch. All right, pop quiz. Pop quiz. A switch looks at what? A switch looks at what when it's determining where to send information? Pop quiz. The answer is MAC address, media access control address, hardware address. Okay? A switch looks at that. So we're going to get a switch to link all of our servers together. Now we're going to wire those up just because. Maybe this is going to be somebody's hang out with cyber sex while we go to sleep. Learn about networking type thing. I'll study a little bit more Japanese and then I'll try to do this in Japanese. Nihongo ga skoshi wakarimasu. Anyways, so we have our corporate servers hooked up. Oh, we gotta have our call center people as well. When I'm calling in, I'm like, my computer's broken and I need the Geek Squad. Like, we need people to talk to, right? So we have our call center. So this is going to be our server work group, our server network segment. This is going to be our call center work group, or call center network segment. All right. And then we're going to use a switch as well for this. Switches are always preferred over hubs. All right. We kind of talked about switches versus hubs. Hubs send all of the data out to everybody else. Something goes to the hub, it gets distributed to everybody else. And then when we get the reply, it goes out to everybody else. It creates what's known as a collision domain, which gets covered later. But we're just going to go with this for now. Oh, we need a switch. I didn't grab a switch. I'm going to grab our switch. We're going to put you here. We'll wire everybody up just for that's not how we do that. All right. Boom. Once again, we're using Cisco Packet Tracer. Cisco Packet Tracer. It's 100% free. You just need to input an email and sign up. Amazing learning tool. All right, so we have our server work group. We have our call center work group. We could have multiple work groups in Best Buy headquarters in Minneapolis, right? All right. But we're going to need a way for these things to talk to each other. And then we're going to have to set up a way for, let's just put this up here, for it to talk to people. So let's see. We'll grab a router. Where's the PT? There we go. All right. So then we're going to grab another switch. There we go. Grab the wrong wire. Boom. Boom. Yeah, we're kind of cheating here by connecting everything via switch. But that's okay. And then we're going to connect to our router. All right. And then from here, maybe we want a proxy server to keep our stuff safe, right? I don't know how to configure proxy servers, but I at least conceptually understand what they are. That'll be end devices. We'll get a proxy server. Perfect. We'll get a proxy server set up. Why did you do that? There we go. Let's see, what's a good way to do this? It only has one Ethernet port. Can we add more? Can I? Yes. Let's see. Let's make sure. We got to power it off. And then features a single Ethernet port that can connect a LAN backbone, which also supports either 6. I don't know 100%. So the PT host and then module provides one fast Ethernet interface for use with copper media, ideal for a wide range of LAN applications. The fast Ethernet network module supports. Hey, that sounds good. Can we install you? All right. All right, and then we're going to need another router. Actually, hey, let's get rid of this. Let's make our network better. That's one of the cool things I really like about Cisco Packet Tracer is like you can adjust and modify things. So you notice we only had the 2 Ethernet ports, right? We're going to need at least 3 because we have 2 switches to connect to, and then we want to connect to our proxy server. And you can see we have our fiber connections here. Yeah, like that's cool, but And then we have one of these old, I don't necessarily know what these are. Like they look like older models of like what we can hook up. But let's grab us an Ethernet port. Is that good? That's RJ11. So RJ11, registered jack 11, is for phones. We don't want that. We want RJ45. Let's see. Single Ethernet port that can connect to a LAN backbone. We don't necessarily want that. Yeah, let's go with this guy. That sounds about right. Is it RJ45? Fast Ethernet. So, yeah, that sounds good to me. Let's just pop in 2 more. We'll turn that on. Remember, always turn things off before you rip things out of components. All right. Connect to you. Hey, we got some fast Ethernet ports. Wait a minute. I thought I installed more than that. We have the proper amount, but that's not quite right. Yeah, we only have 2. I thought I installed 4. 1, 2, 3, 4. Where's the mistake here? We're good. We're good. We're good. All right, we have 2 ports here. So let's get another router. Good, good, good. All right, and this router is what's going to connect to that. So this is our proxy server. We're going to have another router for getting our traffic out and then receiving traffic in. At least I think that's conceptually like where we want to go. And we'll get you. Fast Ethernet. Fast Ethernet. Good. All right. So we have it to where people can come in. But we want to set it up to where our branch offices are. Let's get back to our study guide. So we're setting up the example of a wide area network. A wide area network where we have Best Buy in Columbus, Ohio. We have Best Buy in Seattle. And we're connecting to our corporate headquarters that we're making over here. Our corporate headquarters has servers with our client data. We have our call center. And then we're going to have a proxy server. So that way, if customer wants to go online to look at all of our sweet stuff and our deals and our devices that we sell, that's going to be in our servers as well. All right, we want to set up a proxy server so that way the server is asking for that data and they can't necessarily hack into our servers with our client data. They're just looking at our website server. All right, so that's how we're going to set it up. And then, let's see. We have internet emulation tools, I believe. My eyesight isn't that amazing. I'm going to reach in here. I think we're going to go with DSL modem, which is digital line subscriber. Like this is what we set up to connect to our internet service provider. Do you have a fast Ethernet? Yeah, we do. Perfect. Perfect. All right. So imagine this. This is internet, right? From the internet, it goes to a router. From router, it goes to proxy server. I don't necessarily think we need this router, but maybe we have firewall set up here. Once again, I'm still new at this, so we're just going with it. Then we have a proxy server, so that way our proxy server is the one asking for the data, makes it harder for us to get hacked from the proxy server. We go to our router. If it's, Best Buy in Columbus, Ohio, and John is wanting to send, Microsoft's team message to Sally, it would go from the proxy server to the router to the switch to Sally. But if John wanted to go and double check some inventory, see if hey, maybe we have some inventory of the new Remarkable Paper Pro 2 at corporate headquarters, it would go through the internet into our internet provider, from that to the router, into our proxy, and then the proxy's asking for that. Also, if I want to go on bestbuy.com, same path, I would be isolated to the website. All right, I wouldn't be able to access the client data, but we're setting this up. So that's how we can create a wide area network. It's very wide geographically. There's a lot of different branches all over the place that want to come in and connect to Best Buy specific stuff. All right. And for fun, we can just set this up to look like it is a little bit more than it is. So we have some computers at Best Buy in Columbus. And then, let's see. We'll go and we'll set up a router. So that router is going to get us out. This router is going to get us out. So let's see what else we could add in there. Get some switches. We'll just grab a switch here and another switch. All right. End devices. We'll get some PCs. And let's just say we need a printer. Where's my printer? Printer. There we go. We got a printer. Boom. We'll get a printer here. Corporate doesn't get a printer. I'm just kidding. I'm just kidding. We'll set up a printer at corporate too. Why not? Why not? All right. Now let's link everything together, right? So first, we need to make sure corporate can print off stuff. Perfect. And the reason why you're seeing red here is I haven't configured the routers. I haven't configured them to talk. Let's see if we can set it up to where it will. Let's see. We'll go into configuration and we'll just turn that on. And we'll turn you on. And I will just turn that on. Let me see. What port are you coming out of? So we're at FA10. 10. Yep, you're on. So that's the interface, FA00. And then FA20. So let's see. FA20 is on. FA00 is on. FA10 is on. So now these things can talk. All right. And we have our printer now. Good to go. So we're all the way connected to the internet here. We have our Best Buy in Columbus. Let's link that all up. Fast Ethernet to the switch. Fast Ethernet to the switch. And then our Fast Ethernet to the switch. And then switch to the router. And then the router is going to go to a emulation device. This is going to be our internet. And you also get internet because I'm nice. Then we'll wire you up. Ooh, I didn't mean to do that. Boom. Wire it to the switch. Wire you to the switch. And then we'll wire you. There I go, pressing the wrong cables. To the switch. And then the switch is going to... I really like those yellow cables. I don't know why. The switch is going to connect to the router. And then the router is going to connect to our internet. And then we need to connect you to the internet. All right, there you go. That's kind of how we can imagine creating a wide area network, right? So we have Best Buy in Columbus, Ohio. We have some computers and a printer. Obviously, we're going to have like a lot more computers. We're going to have phones. We're going to have Wi-Fi. We can set all of that up as well. I'm just trying to make a quick example. We have Columbus, Ohio's Best Buy. We have Best Buy in Seattle. And then we have Best Buy headquarters in Minneapolis with all of our stuff. And this goes to show how we can create a wide area network with a multitude of small local area networks that are disparate, that need to connect our corporate headquarters, servers, our call centers, you know, things of that nature. So that's how we've created a wide area network with Best Buy. But wide area network can also refer to the internet. You can think of the wide area network as anything that's big enough to where it's geographically wide in how it is. All right. So, perfect. I think that's a good example. What do you guys think? Let me check the comments. I haven't been looking at that at all. Expert out on having any, but hey, it doesn't hurt to look. Let's see. Hey, I'm sorry, Chris loves tofu. So like a proxy server isn't a need, but it really helps us with security, right? Because we're using a server in the middle of all of our important stuff, as far as I've come to understand. Yeah. So the server is acting on behalf of the client that is further out. So if somebody with bad intentions wanted to hack into our network, that proxy server does all of the work on behalf of them. So it makes it a lot more challenging for them to go and access all of our big data. And how often do I host this? Well, I'd like to do it once a week if that's possible. And I really appreciate you being here. Chris Loves Tofu. All right. I hope you have a good night tonight. And, we'll catch you in the next one if you have some time. But let's see. Let's get our CompTIA study guide back up. I'll toss out a heart there. So we're on to personal area network. All right. And once again, we're in chapter 1 of the CompTIA Network Plus study guide. So personal area networks. So that's for close proximity connections. And personal area network is PAN, P-A-N. All right. These are seen with smartphones and laptop in a conference room where local connections are used to collaborate and send data between devices. Yeah, he goes on to explain that while personal area networks can use wired connections such as Ethernet or USB, it's more common that short distance wireless connections are used, such as Bluetooth, infrared, or Zigbee. I've actually never heard of Zigbee before this class, so I'll look into that real quick. Personal area networks are intended for close proximity between devices, such as connecting to a projector, printer, coworker's computer, and they extend usually only a few meters. So my interpretation of this is something to the effect of, do you know when you go to Verizon or AT&T or your cell phone carrier and you have to transfer all of your data to your new phone? I would think of that as kind of like a personal area network. Or if you want to screen share your phone to your TV, that would be a personal area network. And he went on to use the explanation of like using Bluetooth. So connecting to my speaker, that could be one as well. All right. I think personal area networks are pretty easy to explain in the sense of it's kind of using short distance technology to connect to something very close to you. So campus area network, CAN, or campus area network, covers a limited geographic area such as a college or corporate campus. The campus area network typically interconnects LANs in various buildings and offers a Wi-Fi component for roaming users. A campus area network is between a LAN and a WAN in scope. They are much larger than local area networks, but smaller than metropolitan area networks or wide area networks. So once again, like the big thing to think about with a campus area network and these other things is that it's all size dependent and task dependent. So like I kind of briefly mentioned it earlier, but we'll go ahead and set up a new example. Try to get something here. And bear in mind, I've mentioned it before, but I'm not an expert. I'm learning as you guys learn. I'm just in week 5, and I'm covering the week 1 stuff right now. So I'm learning as we go too. So campus area networks. So campus area network. Let's talk about like a college. We might have the science department. And then science department is going to be broken into like the physics and then chemistry and let's see, biology. So it might be campus, science department might be physics, chemistry, and biology. And then what else is that college? Like, let's see. I'm in college right now. I should know this. And then we might have the math department. And then with the math department, we have, let's see, geometry. and then trigonometry and algebra. All right. So we might have those. I just like that. Go away. Backspace. All right, perfect. So we have the science department. We have the math department. And let's see. What else should we have? What else? What else do we have? What am I interested in? We could have computer. Yeah, we can have yeah, let's go computer. Why not? So we have the computer department, and then we'll have, like, let's just say cyber security, and then we have, let's see, cybersecurity, networking, and let's see, what's the name of the people who actually build the computers? It's like engineering. Yeah. Networking. And then we'll just do physical. Like, they actually work on the computers. Yeah. And let's just say that's all of the departments for our whole campus. Well, we might want to link those up together. And let's start with our networking devices. We know that to talk to different networks, we need routers, right? So we'll get our routers, and that'll be for our science department network. And then we'll get our router for the math department. And then we'll get our router for the computer department. All right. We don't want this router. That router's ugly. Yes, delete you. We'll get the PT router. Nice. So we have our routers, and then those are going to connect our different labs together. Maybe these labs are located in different sections, so we're going to need routers for them too, right? So we might need a router so that way we can talk from the physics department. We'll need a router so we can talk from the chemistry department, and we'll need a router for the biology department. And the same thing applies everywhere else. And so we'll need a router for geometry, a router for algebra, a router for trig, and same thing over here. Cybersecurity needs theirs. We'll do it for our physical computer engineers. Actually, there we go. We'll get rid of physical. We'll call it engineering. Yeah. And then we'll get a router for our networking. Let me get OBS back up so that way I can see. All right. You've been working on AD and you hear that proxy server is the way to filter some of that stuff. Yeah, exactly. Yeah, exactly. Yeah, on Pacific Standard Time. Oh, okay. Yeah, IoT stuff. Yeah, well, haven't gotten to that yet in our networking class. Um, yeah, AirDrop or Bluetooth. So, yeah, I think AirDrop and Bluetooth both classify as personal area networks if we're really thinking about it. Because AirDrop is exclusive to Apple, if I recall correctly. I'm a Samsung fan. I'm sorry. And yeah, I think with AirDrop, you can have it to where you can connect to other Apple users immediately around you so long as they have that enabled. But yeah, I think as far as at least the reading's concerned with the CompTIA Network Plus study guide that we've covered, that AirDrop and Bluetooth are a matter of personal area network or PAN. Okay, so we have it set up right now to our whole campus. We have the science department, the math department, and the computer department. And within those departments, which may be in different sections of the campus, like maybe completely entirely different buildings across the whole campus. All right. We might have the physics lab, we have the chemistry lab, we have the biology lab. Let's get that hooked up right. And then over in the math department, which may be a completely separate building, we have geometry, algebra, and trig. And then maybe we have our computer science department, and maybe that's broken into like cybersecurity, engineering, and networking. Either way, we have different LANs that are all connected. Let's see. You get a router, you get a router, you get a router. Yeah, exactly. Everybody's getting a router. So, yeah, we're just assuming that, hey, maybe we have in our trigonometry lab, for example, that's all inside of the math building. Let's just assume that they're all inside the math building. And then we want to be able to route traffic from our own trigonometry network into the geometry network and then into the algebra network. And then those can go to our exit gateways, which would be our router here for the entire math department. And we can connect these together so that everything can talk. That's awesome, man. I'm glad you're going back to school. Yeah, I'm in school right now, going to college for my degree in cybersecurity. So that's awesome. Good for you. All right, let's go ahead and work on connecting. Oh, yeah, we need our serial connections here. Being uncooperative today. Let's see. Oh, that's why. We have an empty router. Let's grab one of the actual good routers. All right, there we go. And then we'll grab our WAN connection. There we go. And then we'll connect you there. All right. So we have our exit gateway routers that are going to connect to the other networks as well. And then we can go about linking up our routers. And we have a problem here because we're running out of Ethernet ports. So we always power off. And then we'll grab an Ethernet port. Got to find the right one. Make sure it's good. Fast Ethernet. That sounds great to me. I'll just grab some more in there. We'll turn you back on. And let's wire you up to there. Do the same here. Same thing applies. We'll turn this off and we'll grab some more ports. Thanks, man. I appreciate it. Yeah, the goal is to get college done, work on these certifications. Right now, just because I'm doing it with college, I'm working on the Network Plus college. Now, I'm glad you appreciate the explanations. I'm working on the Network Plus for the CompTIA certification. And then when I get some free time, I'll start working on the A Plus and then the Security Plus. And we'll see from there because those certifications are really good for just learning what's what. And then you can get your more specialized certification like the Cisco certifications and things of that nature. So let's finish wiring up our network here so far. And I think I grabbed the wrong interfaces. Get rid of you. Okay. Let's see. Provides fast Ethernet. Yep, that sounds good to me. And let's turn you back on. And let's route you. Fast Ethernet. Okay. So we're kind of getting the idea here, right? So let's just say that this is its own isolated building. we have a gigantic campus. Maybe we're super blessed with a lot of money. And then, so this is its own building here. Science has its own building, math has its own building, and then computer science has its own building, right? And then inside that building, we might have different labs or different floors. So maybe floor 1 of our entire building has the local area network for physics. Maybe floor 2 has the local area network for chemistry. And then maybe local area network 3 has, or floor 3 has our local area network for biology. And then we have our router for the entire math building. And then from there, we have local area network for geometry, algebra, then trig. And we can go ahead and set up our router for the computer science division, which will be over here. I was a bad boy. We need the power off. Grab some more ports for that. Now let's start wiring this up. And of course I grabbed the wrong ports. So click on you, make sure. No, I don't think that's right. Let's just grab 2 of you, see what happens. Oh, we need the power on, can't forget that. Fast Ethernet to engineering. Fast Ethernet to networking. All right. So yeah, determining the right Ethernet port, that's a good question. So the thing with routers and switches is that they can recognize which network is what because you assign that to them. Going into the configuration is something we'll definitely do in later chapters, but you can assign a network to an interface on a router. So what I could do here on the router's different interfaces, because we have the different Ethernet ports, I can assign a network to this Ethernet port. I can assign a network to this Ethernet port and then assign a network to this Ethernet port. Then all of the devices underneath this network will have their own. Yeah, we can definitely get into firewalls. I haven't covered that yet in my college courses yet. I appreciate it. I love Network Chuck. He's so good. That's the goal, is to get to his skill level someday. We'll see. We'll see. I appreciate it, though. Thank you so much. So yeah, subnets and VLANs are their own different things, but right now, at least as far as our campus area network is concerned, we're kind of just setting this up as an example. So yeah, but going back, for our router, we can program the different interfaces on the router to represent different networks. And then in this network that we're making, we can assign our own IP addresses or create our own server to assign IP addresses dynamically within a certain range. It all depends on what we're really wanting to do. But right now we're just going over, at least conceptualizing, what a campus area network is. My goal is to work with the CompTIA Network Plus study guide and go through it bit by bit. And that way, if anybody is studying for the Network Plus, that way they can at least have something to follow along with if they reach a point where they can't figure out what they're talking about. Because there's definitely things I still don't know. As I mentioned at the beginning of the video, I'm in week 5, and this is over the week 4 stuff. So, and this is all brand new to me. I don't come from an IT background, and this is my very first core class in computers with college. So we're definitely going to make some mistakes and learn as we go together with it. All right. So as I was saying with this kind of conceptualizes our campus area network. Let's see. Let's move on to the next thing in the CompTIA study guide. And we'll go to studio mode. There we go. That way I can read better. I'll back up. All right, so storage area network, or SAN. It's designed exclusively by and for storage systems. Storage area networks interconnect servers to storage arrays containing centralized banks of hardware or similar storage media. So storage area networks are only found in data centers, do not mix traffic with other LANs. So a storage area network, we kind of set it up with our Best Buy example. So with a storage area network, we'll just go ahead and grab a bunch of our servers, which are our end devices. We're going to have server, 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 server. No, I don't want to delete you. So we'll just make a small, quick example. So a storage area network is going to look something like this. And then we're going to interconnect them with a switch. We're going to grab our Ethernet cable. And we're going to connect all of our servers to the switch. All right. So we've essentially gone about setting up our storage area network, but it needs a way to talk out to things. So we would have our switch, and then our switch would connect it out to, potentially speaking, our router. We'll grab the PT router. All right. And then we'll interconnect that. So this is essentially speaking going to replicate our storage area network. It's exclusively for storing information and data, at least in accordance to what they're kind of saying here. Stands are usually only found in data centers and do not mix traffic with other LANs. The protocols are designed specifically for storage, with fiber channels being most prevalent among the ISCSI. I don't know what that acronym stands for. Let's hit up the Google. ISCSI. ISCSI. Service. Let's see what that is. So, Internet Small Computer System Interface. Google says is a storage networking standard that enables block level access to storage devices over standard TCP/IP networks. So yeah, it sounds like it's a protocol that we're going to get into some more details with later. And let's see. So yeah, with Chris loves tofu. So with a switch before a router. So what a switch will allow us to do is, if we were to have multiple computers, right? What we're trying to do with using a switch before a router is, let's just say this is James, and then this is Sally. Right? And then we can have whoever here, and then whoever here. All right. So we have our 4 computers, and we want them to be able to talk to each other. The reason why we would use a switch in the front instead of having a router is that when we have multiple network segments like this, so imagine I copy this. I don't know if I can copy this. Hey, that worked, kind of, not really. Can I undo? Yes. That doesn't work how I want it to. Still learning how to use Cisco Packet Tracer. But imagine we have this network segment, and then we have another one over here and another one over here. If James wants to talk to Sally, if I were to use a router, that's going to utilize IP addressing. Whereas if James wants to talk to Sally here, we're using MAC addressing. And then the thing is when we have routers involved as well, if the router is in charge of doing all of the communication between all of these nodes, all of these computers, that creates a lot of overhead. So if James wants to talk to Sally and X person wants to talk to James and then Y person wants to go to the internet, that's a lot of overhead work for the router. So what a switch allows us to do is minimize the amount of work the router has to do. So that way the router has free access to other networks and other internets, because the less traffic we have going across larger connections, the faster the connections are. That's bandwidth. So we're trying everything we can to increase the bandwidth on our router, so that way there's more room for it to move traffic. So we're just breaking the network down into smaller and smaller pieces. All right. So just going over the storage area network, that's what this kind of looks like. We have a switch that links a bunch of storage devices together that's accessible via a router. At least that's how I'm kind of conceptualizing it. So software-defined wide area network. It says a software-defined wide area network, or SD-WAN, is a virtual WAN architecture that uses software to manage connectivity, devices, and services, and can make changes in the network based on current operations. SD-WANs integrate any type of transport architecture such as MPLS, LTE, and broadband internet service to securely connect users to applications. SD-WAN controllers can make changes in real time or add or remove bandwidth or to route around failed circuits. SD-WANs can simplify wide area networking management and operations by decoupling the network hardware from its control mechanisms. So that one may sound a little bit more complicated, but let's take a real look at what that looks like, right? So I'm just going to use routers for this examples. Yeah, exactly, avoiding collisions. Yep, layer 1 is the bare wire versus bridge switches and bridge, which are layer 2, and routers are layer 3 in the OSI model, the Open Systems Interconnect model. So getting into software-defined wide area network, we're going to use routers to emulate the internet. All right, so we're just going to grab a bunch of these routers. Let's get this kind of set up. It's going to be a little bit all over the place, but that's fine. And yes. So imagine all of these routers are just like a small section of the internet. We have a whole bunch of different places. We have like servers for google.com. We have servers for youtube.com. We have servers for Facebook. We have all sorts of different services and servers across the entire internet. So software-defined wide area network, what that's kind of doing for us is that software is defining, more or less speaking, the routing protocols here, which creates a virtual WAN architecture. Actually, let's backtrack. Let's try to do that in a better way. SD-WAN's integrated type of transportation architecture. Just real time. Add or remove the bandwidth or route around failed circuits. So yeah, let's not use that example per se. Let's just say I own a restaurant chain. Let's just say McDonald's, for example. So a software-defined wide area network. What we're essentially doing is we're creating a way for data to travel in case routers fail. So we can sort of like link things together, which would be pretty time expensive, at least as far as the video. And what software defining the wide area network would do is if this router were broken and we go from this to here and this to there, then this to here, like it's talking to multiple different branches. And this router broke, and this router is what we use to connect to here. The software-defined wide area network would allow us to route around that. Maybe this would have been the fastest way, but if this one's broken, maybe we go over here, down, and then to this guy here. All right. That's how I'm kind of interpreting the software-defined wide area network. But let's go and just see if Google can give us a better explanation so that way I can make sure we're doing it right. SD-WAN. Yeah, so software-defined wide area network is a virtualized networking approach that decouples network control software from underlying hardware to simplify management, increase flexibility, and reduce cost. It uses centralized control to securely manage diverse transport links, MPLS, broadband, 4G and 5G, and optimize traffic routing across branches and cloud applications, according to YouTube. So software-defined wide area network, reduce costs, replace or complements expensive MPLS. Let's check and see what MPLS is. I recognize the acronym. I don't remember it, though. Let's see. MPLS. Okay, multi-protocol label switching. Labels rather than long network addresses. Yeah, we'll definitely grab into that at a different section. So I think SD-WAN, or software-defined wide area network, is something that's kind of integral to like cell phone communication, and then like routing around that if like a tower fails and things of that nature, to essentially, instead of having to utilize physical routers to go from place to place, use software to go around those routers if you need to. Okay. And then we go into multi-protocol label switching, or MPLS, which is definitely something we're going to add to our list. So if we've been following along with the list, let's start adding some of our stuff, which is our PAN, our personal area network. And then we have our MAN, which is our metropolitan area network. Yeah, we got that. We got our CAN, C-A-N, which is our campus area network. And I think we've covered all of them there. Perfect. All right. Multi-protocol label switching. I spelled, yeah, I did. Multi-protocol label switching. All right. So the term multi-protocol label switching, MPLS, as used in this chapter, will define the actual layout of what is one of the most popular wide area network WAN protocols in use today. MPLS, multi-protocol label switching, has become one of the most innovative and flexible networking technologies on the market, and it has some key advantages over other WAN technologies. Physical layout flexibility, prioritization of data, redundancy in case of link failure, one-to-many connections. Multi-protocol label switching, MPLS, is a switching mechanism that imposes labels or numbers to data and then uses those labels to forward data when it arrives at the MPLS, multi-protocol label switching network. All right. So before we take a deep dive into this, I'm going to take a quick hydration break. All right, I'll be right back. Thank you, everyone. All right, we're back. We're back. Let's go and double check, make sure the stream's going all right. Let's see. How's everyone going? Yeah, just about to get started back at it. How long have we been at this? All right. So let's see. We've been at it for about 2.5 hours. Let's get some more out of the way. We're just about, let's see, just about a little over a third of the way done with chapter 1. And let's work on it. Let's work on it. Because some of the stuff is still challenging for me to understand, like multi-protocol label switching. Yeah, so we'll read through the study guide and see what else we get here. Okay, so we left off that multi-protocol label switching is a switching mechanism that imposes labels or numbers to data and then uses those labels to forward data when it arrives at the multi-protocol label switching network, as shown in the figure. So let me get back over to it. Hello. Glad to see you're still here. Chris loves tofu. I hope you're doing good, man. All right, let's check it out. Let's go to my desktop capture. So this is the figure that they're showing. They're showing that we have a corporate office, and then we have the multi-protocol label switching network, the logical connections between sites, and then our branch offices over here. So we'll get this back to the side to avoid copyright. I don't know how all that works yet, so don't want to risk the biscuits. All right. So each router assigns labels to data when the data heads towards the multi-protocol label switching cloud. The labels are assigned on the edge of the multi-protocol label switching network and forwarded inside the MPLS, multi-protocol label switching. I'm going to keep repeating the acronyms and like what they mean. So that way we can kind of reinforce and hold on to that information. One of the things I've absolutely loathed about trying to do research is like, so I've studied a bunch of stuff on YouTube with regards to like the CompTIA Network Plus. Professor Messer is fantastic. I've enjoyed his stuff. And then after I started doing the deep dive into those things, all I ever see now is like people with, this is how I got my CompTIA Network Plus certification in 3 months. Follow these study steps, but they never dive into the data. And like, it's always short, like, these are my study methods. I looked at Professor Messer. I looked at the study guide. I went and did these practice tests, but nobody dives into and like puts themselves out there for like, here's the material. Let's work through understanding it together. So that's what we're going to try to do. So yeah, let's get back to it. Sorry for that digression there. Let's get back to it. It's a desktop capture. So let's see. The labels are signed out of the edge of the multi-protocol label switching network and forwarding inside of the multi-protocol label switching network cloud is done solely based on labels through virtual links instead of physical links. Prioritizing data is a huge advantage. For example, voice data could have priority over basic data based on labels. And since there are multiple paths for data to be forwarded through the multi-protocol label switching cloud, there's even some redundancy provided as well. So let's see. Multi-protocol label switching seems like it's more like quality of service type thing, towards like certain services are prioritized. Yeah. Let's double check the Google and see if we can't find any resources on YouTube to reference real quick that might give us some better explanation. Let's see. So just the AI overview, let's read through that real quick, see if that gives us a better understanding. So it says multi-protocol label switching, MPLS, is a high-performance networking technology that directs data using labels rather than long network addresses. Speeding up network traffic and improving efficiency, this operates between Layer 2 and Layer 3 of the OSI, which is the Open Systems Interconnect model, making it ideal for creating secure. I can bring that over here. Making it ideal for creating secure, high priority, and reliable virtual private networks for voice, video, and critical data. Let's see, key functions of multi-protocol label switching. Label switching. Instead of checking complex routing tables at every hop, routers use short labels to move data, reducing processing time. Label switching paths. Multi-protocol label switching establishes predetermined paths for data to travel across the network. Traffic engineering. It allows network traffic administrators to manage traffic efficiently and assign priorities to different types of data. Fast reroute. Provides sub 50 millisecond protection switching to instantly restore connectivity if a node or link fails. Key concept. Label edge router. Positioned at the edge of the network, these routers assign labels to incoming packets. Label switching routers. Located in the core, these routers forward packets based on the assigned labels. And then there's the advantages, the disadvantages. So benefits, we got improved performance, security, scalability, quality of service. Yeah, that's something I kind of mentioned, is quality of service. Let's see, disadvantages. High cost, dependency on service provider. That's interesting. Requires specialized, often slower service provisioning and relies heavily on a single provider. Limited coverage. It's a closed system. Let's see. Okay. Yeah, this seems like it's more, in regards to conceptualizing it. It's layer 3 VPNs, virtual private LAN service. Okay. And then traffic prioritization. So, yeah, I think we're getting kind of a basic understanding of it. So, MPLS, which is multi-protocol label switching. What it allows us to do is prioritize traffic, giving it different priority levels based on what it is. And based on what it is and what it's been assigned as its value, determines how that traffic is forwarded. And then it also gives us the ability to change how traffic is routed depending on the labels as well. So I can see that being effective in regards to a security standpoint, whereas if anything is flagged with that, it gets sent somewhere else to be assessed, which would be like our intrusion prevention system, our intrusion detection system. I can see that, which that gets covered later. So let's keep going through. I think we spent enough time on multi-protocol label switching. So our next topic is multi-point generic routing encapsulation. And it says the multi-point generic routing encapsulation. Oh, did we add? Yes, we got to add that to our list. So it is lowercase m, then GRE, which is multi-point generic routing encapsulation. So at least as far as like computing terms go. So I have my notepad here. And when we're talking about encapsulation, let's just say we have data. This is our data. All right. So what encapsulation is just a matter of we have a program or device that will then add data to the front and or the back. So let's actually change that up. We'll change the colors. Let's go with red. So it's going to add data. Then it's going to potentially add data. Like I've seen in some cases where data is not added to the end of it. But encapsulation is just a matter of data is added. And then typically we have our frame check sequence over here that will get modified or added to. And that's what encapsulation means. We're just kind of wrapping data around something. So let's go in and explore what the book says our multi-point generic routing encapsulation is. So it's saying that the multi-point generic routing encapsulation protocol refers to a carrier or service provider offering that dynamically creates and terminates connections to nodes on a network. Multi-point generic routing encapsulation is used in dynamic multi-point VPN deployments. The protocol enables dynamic connections without having to pre-configure static tunnel endpoints. The protocol encapsulates user data, creates a virtual private network connection to one or many nodes, and when completed, tears down the connection. All right, so let's try to think about this a little bit. It seems like a lot of fancy words, and I think there's a way that we can go about making it easier to understand. So, things to break down from this is it's used in dynamic multi-point VPN deployments. So multi-point meaning we're connecting to different things at the same time. Virtual private network. So virtual private network, all we're really doing with that is we are essentially speaking using our IP address to connect to another network, and then that network is connecting to our application or our endpoint. So what multi-point generic routing encapsulation does is it wraps around the data and it allows for us to connect to and maintain a connection, and then it also helps with breaking down that connection when it's done. That's how I'm interpreting it. So network architecture, peer-to-peer or client-server. All right, let's take a look at that. We've developed networking as a way to share resources, information. How that was achieved directly maps to the particular architecture of the network operating system software. There are two main network types you need to know about, peer-to-peer and client-server. And he says that it's tough to tell the difference just by looking at a diagram or even checking out live video of networking humming along. Differences are pretty major. They're just not physical. They're logical differences. You'll see what I mean in a bit. So peer-to-peer. Computers connected together in peer-to-peer networks do not have a central or special authority. They're all peers. Ah, that makes sense. So yes, yeah. All right, let's set this up in Cisco Packet Tracer. So peer-to-peer. All right, let's grab our computers. No, I don't want to delete you. So we have our computers. Let's space these out a little bit. All right, and then we're going to grab a switch because they're way better than hubs. I'm going to grab a switch. We'll just grab the switch from here. And then we're going to connect them together. So into the Ethernet port, into the switch, into the Ethernet port, into the switch, into the Ethernet port, into the switch. And then lastly, into the Ethernet port and into the switch. All right. Hydration time. So we've set up, essentially speaking, a peer-to-peer network. There's not a centralized computer with special authority. They're all peers. So when it comes to authority, they're all equals. The authority to perform a security check for proper access right lies with the computer that has the desired resources being requested from it. So what that means is if we have computer A and then computer B and then computer C and then computer D. So we have computers A, B, C, and D. All right. And then computer C has the goods. So we're gonna say that computer C has the goods. So computer C has a file or has something that another computer wants. Maybe I'm on computer B and I want to access a document that's saved to computer C. All right. What we're saying here is that when computer B wants to request the file or document on computer C, it's up to computer C to determine if computer B can have it or not. All right. So the authority to perform a security check for proper access rights lies with the computer that has the desired resource being requested from it. It also means that computers coexisting in peer-to-peer networks can be client machines that access resources and server machines and provide those resources to other computers. This actually works pretty well as long as there isn't a huge number of users on the network. If each user backs things up locally, and if your network doesn't require much security. So essentially speaking, in this system here, like it'll work out pretty well if I just have 4 computers and that's all I have. And I just want to be able to share files between the 4 computers. Like there's not a lot of security or authorization in place to make sure that, hey, like we're not having traffic coming into our network and then they're just able to like grab stuff up. All right. So it's saying if your network is running Windows, Mac OS, or Linux in a local LAN workgroup, you have a peer-to-peer network. And then it gives us a little diagram of what that looks like. So with our diagram, we have it essentially set up the same, except for I used a switch because hubs suck. And I have a video on why and how hubs suck. So up to you if you want to watch that one. Oops, let me get that back. Where'd you go? Every time I minimize it, it disappears. So pop you back up. All right. So we have our little diagram here, and let's move this off to the side to prevent copywriting. And then it goes on to explain, since we're in a peer-to-peer, it's not all sunshine. Backing up data is critical. It's vital. Let's see, we can skip past some of that to forego copywriting. Yeah, and it seems like one of the problems with having a peer-to-peer network like this is that each computer has to have the login access credentials of each other computer if you are setting it up to where there is at least some slight security in place. As we kind of saw with our hub network that we have in the study guide. So he goes on to explain, because security is not centrally governed, each and every user has to remember and maintain a list of users and passwords on each and every machine. Worst, some of those all-important passwords for the same users change on different machines, even for accessing different resources. So yeah, if you don't have a server set up in place, yeah, check this out. So if I were to have instead a server or a workstation that's in charge of the security and user accounts and everything like this, what I would have to do if I was on computer B and I wanted a file on computer C, I'd have to remember a login and a password on computer C that I would use to, essentially speaking, be able to get that file. Whereas if I were to have a server would actually make everything way better. And devices server. If I were to have a server as my central authority, if you would, a server that has the central authority, that shares everybody's user information. Like Thomas has his own login profile. James has his own login profile. Jeffrey has his own login profile. Sally has hers. And the server would store all of that user data. So that way, if I was on computer B, I'd log in, and if I wanted to access computer C, the server would have the login data to validate me to access the resources on computer C. I wouldn't have to remember the specific login credentials for computer C. But another thing that a server would give us that's even better is we can create files in the server and then back those files up to the server, so I wouldn't even have to bother computer C. So what we set up before here is a peer-to-peer network. All right, the next point, hey, we're at the halfway point. The next thing is client-server networks. So it says client-server networks are pretty much the polar opposite of peer-to-peer networks, because in them, a single server uses a network operating system for managing the whole network. A client machine requests for a resource goes to the main server, which responds by handling security and directing the client to the desired resource. So let's go about setting up our server like we had it just a second ago. And then we'll go about wiring that up. All right, we're set up. This happens instead of the request going directly to the machine with the desired resource, and it has some serious advantages. First, because the network is much better organized and doesn't depend on users remembering where needed resources are. It's a whole lot easier to find the files you need because everything is stored in one spot. On that specific server, your security also gets a lot tighter because all usernames and passwords are on the specific server. That's just what we talked about. And then you gain scalability. So I can add even more computers to this, maybe another switch with more computers. And then all of the data, all of the login information gets stored on the server. Let's see. Yeah, and it goes over, it basically shows a figure of what I mentioned. Like the server stores all of the users and passwords, and you can also program the permissions in there. Like maybe people can only look at certain folders. People can only look at all the folders. People have the ability to look at them and modify files. It can really depend. Like you can program your server to give all sorts of different permissions to it. So physical network topologies. All right. So let's go ahead and delete this. And we'll move on to that one. So he goes and compares that, a topographical map, right? If you look at a topographical map, it's going to show the shape of the terrain and the way the landscape physically looks, all right? It defines special characteristics such as all the workstation and other devices located with precise arrangement of all the physical media such as cables. So Cisco Packet Tracer, as we're looking at what I'm making on here, is a great way of visualizing the physical network topology. All right. Logical topologies are a little bit different. So when I set up Cisco Packet Tracer, and then we've done the example of like how data has moved through the network, that's your logical topology. It shows exactly how data moves through a network. They're very much so similar, but they're also different in the ways like you can get a grand holistic view of every device on your network with a physical topology. With a logical topology, you're just seeing how data moves. All right. And now we're going to go over the different types of topologies, like a bus topology. So check it out. Check it out. So with a bus topology, you're going to, essentially speaking, let's see how I can think about editing this. Okay. All right. I got to use the brain sometimes. So I'll read through this and we'll try to demonstrate what we're talking about here. Another thing I might do is pull up this. All right. So a bus topology is a type of topology that and it's the most basic one of them. Yeah, he complains about it. So it has two distinct and terminated ends, with each of its computers connecting to one unbroken cable running the entire length. So we would, back in the day, attach computers to the main cable, also known as the backbone, with wiretaps. And they kind of sucked because one of the things is if you have an issue with your backbone, your main wire, and let's go and look at the example they show. All right. So we have our backbone, which is a singular wire that connects all the way from point A to point B, and then different devices connect into that backbone wire. One of the problems is if, somebody's pushing a cart and somehow breaks the wire, or we have an issue where something happens to this backbone, we lose connectivity to whatever side isn't connected to the rest of the network. So if we only have these two computers here and our servers here, if there's a cut in the line here, these guys cannot access our server. There's no redundancy built into it. They also can't print or anything. They just talk to each other, maybe, but they can't connect to the server or anything else on the network. And that's what they're calling the bus topology. Yes. So even though all computers of this kind on this kind of network see all the data flowing through the cable, yeah, that's another one of the problems. Is like you have a major collision domain there, where a bunch of data is going through that cable all at the same time, and you're taking up all of the bandwidth or the ability to communicate on that cable. Yeah, it's easy to install and it's not expensive because it doesn't require that much cable. Yeah, exactly. But it has a lot of drawbacks. It's hard to troubleshoot, change, or move, and it doesn't really offer much in the way of fault tolerance. Exactly. So let's set up something. I don't think I have any connectors that really I can use, but we can YOLO make something. Let's see. Yeah, we'll just make a little something that illustrates the picture of like what a bus topology looks like. So imagine these are just simple connectors into our main wire. We have our main wire that I'm trying to pick the yellow. We have our main wire that goes all the way across our network. And remember, we've covered switches before. Switches are smarter devices than hubs. They can pick and choose who the information goes to based on the MAC address, the media access control address, the hardware address. All right. So let's just say we have a few PCs here. Actually, a better illustration of this would actually be to use hubs, as much as I hate hubs. and we can see some chaos. We can see some chaos. I'll set up some chaos for us. Let's go to hubs. You'll truly see why they suck here in a second. I'm excited for this. Let's do this. Let's set up some hubs. Hub, 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 hub. All right. And now let's set up some computers. So we have some computers. We have some computers. I think this will be a good example. You'll see. You'll see the chaos. It'll be fantastic. All right. And let's set up a printer too. Why not? Why not? Come here, printer. All right. Let's get some more computers over here. Fantastic. All right, let's get another printer. All right, bear with me. We're going to wire it all up. All right. So Ethernet port to hub. Boom. Let's get you looking a little bit prettier. I like organization. No, it's not OCD, I promise. It's just organization. All right. Let's get it. So Ethernet port to hub, and then Ethernet port to hub. All right. This is our backbone. This is our backbone. Our backbone's going to stretch from hub to hub. From hub to hub. And then lastly, from hub to hub. All right. So let's get this set up to where it's nice and horizontal. I have a whole screen. Let's widen this up a bit. So let's get these guys over here. All right. Let's set it up. Yeah, just bear with me for a second, guys. We'll get this all set up and you'll see the chaos. All right. Boy. Fast Ethernet. Fast Ethernet. Fast Ethernet. And then Fast Ethernet. Yeah, we used all of that. All right. Okay. So we have it set up, right? We have it all set up. And you can see how we have our backbone that goes all the way across the network, right? This is our backbone. This is the bus topology. All right, we have it kind of set up like that, except for we've added a few more computers, but we have our backbone. You can see now that if we had something go wrong with the line right here, if something happened right here, all of these computers stop being able to function with the network. And we can also like make it even better. Let's add our router here. And then let's see. I think we'll have to get rid of something. Let's see. Do we have any more open spots? Oh, look at that. We have one more. And let's just say this gets us to the internet. If something happens right here, all 6 of these computers lose all functionality. And this is the bus topology. This is the bus topology. All right. So we can see that if something happens right here, these guys lose the ability to go out to the internet via our router. All right. Let's test and see if I don't configure the IP. Let's see. Hypothetically, we should be able to get a packet from here to here. Okay. And I'm guessing not. We haven't assigned anything. So let's see. Nope, we don't want that. We'll go in the desktop, IP config, 192.168.1.1. And then we'll go over here, desktop IP configuration, 192.168.1.2. All right, now let's give it a try. Boom, and boom. Failed. Oh, let's take a look, see what happened here. Let's do our simulation and play. To the hub, I'd expect it to disperse across everything else. It did not go to our next hub. Why is that? Let's see, configuration. So learning as we go. Let's go back to real time. See what the problem is. So we have Fast Ethernet 0 is showing as down. Configuration, hub 3, device clock. Yeah, that's fine. Not seeing anything off the top of my head that's shooting any red flags. What if we powered down, powered on? Or do I have to make it a switched network? Let's see. Let's see if it'll send it out if I have a switch instead. Let's do delete. Yes, we'll delete the hub. Let's yoink a switch, because switches are smarter. I was expecting to get some kind of chaos, but unfortunately we didn't get any chaos. We'll see if doing a switch every other will give us the chaos or not. Boom. And then let's see about linking my switch up to my hub. Do we get connectivity? Hey, it looks like we do. All right. And then do we have to change you out for a switch? Let's check and see. Network devices, switches, and we'll grab a switch, put you here. We'll grab our wires. It looks like everything's connecting fine. I was expecting a total cascading effect of chaos, but for whatever reason, it didn't want to cooperate with me. Maybe we'll learn about that later. Hey, look, I'm learning as we learn. I will reach a point to where I don't have the answer. And we're going to Google that after a little bit. We're going to see. All right. Let's see. Let's see if we get connectivity. It looks like we're coming online slowly but surely. And one link at a time. All right. So we've configured the IP configuration here, right? 192.168.1.2. And we've configured this one, if I recall correctly, 192.168.1.1. All right. So let's give this a try on our PCs that we have not configured. See what happens. So we have not configured you, and we have not configured you. Let's see if we get a failure. So no functioning ports. I don't know if that's just a matter of Cisco Packet Tracer or what that is, but that's okay. We configured you, and we configured you. Let's see. Hey, we got success. Let's take a gander at what that looks like in the simulation. Play. So we got the switch. I'd imagine the switch is going to be semi-intelligent, but we haven't really configured everybody. Yeah, look, there we go. We go to the hub. That should spurt it out to everybody. We'll see. Yeah, that does the chaos. And then the switch is smart. We should send it to the hub. So we get it at the hub, and then we should go to everybody. And this guy should be like, yes, that's for me. We should get green checkbox. Or, yeah, it's fine. And we're going to get the response. Sends it back. The hub's going to be like, hey, let's tell everybody. Yeah, and sends it along. The switch is like, hey, I'm smart. Let's send it over here. Where'd it go? Or is this the response? Let's try this. Let's see what this guy is. It's going to go out to everybody and then to the switch. All right, the switch got it. Everybody recognized it wasn't for them. The switch sends it off to the hub. Hub got it. Hub's going to bleh to everybody. Sends it to the switch. Switch gets it, and we should go up here. Yes. Perfect. And we get our checkbox. All right. So let's delete all of these. Hit play one more time. I think that's just the switch trying to figure out who's who. All right. So we're going to grab our data. And then one last time, we're going to send it here. Yeah, we're mixing everybody up. So we got the purple. We're on the purple. Purple message goes to the hub. Hub's going to bleh to everybody. And then the switch is going to be smart. Send it to the hub. Hub is going to puke it out to everybody. Perfect. And then our guy is going to be like, oh, that was for me. Cool. Let me send a response. Hey, I got that, buddy. Then the hub again is going to be like, hey, let's send this to everybody. Switch is a smart guy. Looks at that MAC address, that hardware address. He's like, oh, yeah, I think that's over here. Because the switch has seen that that MAC address has come from this direction before. And he's going to send that off. Perfect. All right. So we can see though, that if something happened to the connection here, check this out. Where's the off button? Let me zoom in. Does the switch have an off button? Actually, I don't see an off button for the switch. Can I mess with you? Configuration. Kind of curious. Just looking through this real quick. So we haven't configured any VLANs for this switch. That's fine. CLI. Channel status is up. Let's see if the switch is recognizing MAC addresses right now. Hey, looky here. The switch is recognizing MAC addresses. That's awesome. Through its Ethernet ports. Perfect. Okay, so we kind of set up the bus topology. But as you can imagine, if I were to say have an issue with this hub, you see how the hub, if the hub broke, we would have issues with this entire piece of the network. That's one of the main issues with having this backbone bus topology, is that if there's a failure in the backbone, the main thing that connects everything together, there's no system in place to have any redundancy at all. And then you can see how there's just tons of traffic. So let's turn this back on. All right. And if we were to configure all of these out, and I were to throw tons and tons of data in there, you'll start to see how this line just gets fuller and fuller and fuller. And then it just creates a ton of work that's on this line. And in turn, we're going to start having collisions with the data on the line. And that's going to be an issue. but there's solutions for that, which I think are covered in the next chapter. So let's start moving on. So, all right. It goes on to explain that even though all the computers on this kind of network see all data flowing through the cable, only the one computer in which the data is specifically addressed to actually gets the data. So another way that this could be set up is that if each of these computers, instead of being on a switch or on a hub, were directly tied into this wire, that's a good way of doing it. And a hub is a good way of representing that almost. All right. But we're going on to the star topology, the hub and spoke topology next. So a star hub and spoke topology's computers are connected to a central point where they're with their own individual cables or wireless connection. You'll often find that the central spot inhabited by a device like a hub, a switch, or an access point. So yeah, that's easy to set up and demonstrate for you guys because we already have it set up. So let's delete that, and then we'll go through and we'll delete these. So delete. And let's just scoot on over here. So this is a perfect example of a star topology or a hub topology. I'm sorry, a hub and spoke topology, because you can kind of see that if we added some more devices here, how it genuinely starts to look like a star or a hub and spoke, like a bicycle tire. All right, let's get that a little prettier. Yes, I'm an artiste. So that's a star topology. All right. So the added benefit of having a star topology is like you have a little bit better of a redundancy system in place in that every single computer has its own individual connection. So if the line here breaks, the whole network doesn't crash. We just lose connection to this one computer. Let's replace this computer, actually. Let's replace that with a server. Let's grab a server. Perfect. All right. That way we can start to envision this. So I have 4 computers, and I have a printer and I have a server. All of these computers are going to want information from the server. That'll be like our login credentials that we covered earlier, right? So we have our login credentials. So I get a username and password set up for me, Thomas. I can log into this computer, this computer, this computer, or this computer because the server has my login, my user information. And we can see, though, that if I were to go log into this computer, but SpaghettiOs, we have a broken Ethernet cable. Oh, that sucks, but it doesn't destroy our entire network. This one computer doesn't have connection, just this one. So I can go onto this computer, log in, it'll go to the server, pull up my user profile, authenticate it, and be like, okay, yeah, you can log into that computer. So that's the star hub and spoke topology right here. And yeah, this is the example they have, which is kind of exactly set up like I have it, right? We have our hub, the dumb hub. The dumb hub does not review anything. A switch looks at the MAC address. MAC stands for Media Access Control, and it's also known as the the hardware address. It's burnt into the network interface card. Remember, the network interface card is this right here, the card that plugs into our PC, right? That gives us internet connection or network connectivity. We also can have the network interface card for Wi-Fi or fiber. All right. Moving on. So he goes on to explain that the star hub and spoke topology is a little bit better in that there's a little bit more scalability So if I have a hub with a lot of ports, like let's see if I do, like if I have a hub with more ports, how many ports do you have? Oh, you only have two? That's more like a bridge. Let's see. What do you have? Cancel. I don't even know what that is. Let's just get rid of you. Looks like we're stuck with you. Can I add more? I can add more. Perfect. So if I want to add more, so let's link you back up, right? Perfect. So if I want to add more, I have 4 slots here that I can go in and let's see. Let's make sure this is it. That looks like it's right. Oh, we got to turn it off first. Always turn it off first. We can add more Ethernet ports. Turn it back on. So it's scalable, right? As in, hey, I want to add more computers. I just get more computers and I plug them in. Like it's just a simple matter of more computers, more holes, and then plug them in and good to go. And then he goes on to explain that a single failure in the cable doesn't crash the whole thing, but we do have a single point of failure in the hub. If the hub dies, you see how we lose everything. We do have a single point of failure here. So that's not necessarily good because then it'll crash our whole network and then we have to go about reassessing our network there. And relatively easy to troubleshoot. If my whole network is down, first thing I'm going to look at is the hub. And then maybe we have to switch out the hub. We get our hub back online. And let's wire up our last computer here just for fun. All right. And then if only this computer is having a problem, but I have connectivity to the rest with the rest of the computers, then I'm pretty sure it's the connection from this computer or it's an issue with this computer. So we've isolated the problem there. But yeah, it is bad with having a single point of failure. Okay, ring topology. Ring topology. So in this topology, each computer is directly connected to other computers within the same network. So that's an issue. It's a pain too. It's a pain to wire. But let's try to get this going. We'll get rid of you. Delete. So here's a ring topology. We're going to set our computers up in a nice little circle as best I can. And we're going to see if we can modify our computers a bit because these ones come only with that network interface card. I don't know if we can add another. Let's see. Yeah, it doesn't look like it. All right. Yeah. It's going to be hard to demo just because of the limitation with this. I can't pull these guys out either. All right. So I can make this work. I can make this work. Cisco Packet Tracer isn't the best for trying to demo this, but I can show you the study guide and what they're talking about. So this is a ring topology. So computer A is connected to computer B. Computer B is connected to computer A and computer C. Computer C is connected to computer B and computer D. And D is connected to C and then A. I'm glad we stopped there before I embarrass myself with the alphabet on stream. But yeah, that's essentially speaking how it's hooked up. The problem with that is if we have a connection go down, then if we're trying to talk from this computer to this computer here, then we have to go all the way around. The other problem is as computers are talking back and forth quite a bit, we're overloading all of the data on those lines, and we can only talk one at a time. So something I covered, which is covered in Ethernet standards, is like full duplex, right? Full duplex is when computers can talk and listen at the same time. But if you're talking in this standard, only one computer can talk at a time. So if this computer wants to talk to this computer over here, nobody else can talk around that connection because these computers are having a conversation. So they have to stop and wait until the conversation's over before they can try to talk. And then when you have all of these guys set up together, you can see how that starts to turn into a headache. So this is the ring topology. The ring topology. All right, let's move on to the next thing. We're over halfway done. So mesh topology. That's also going to be hard to enact on Cisco Packet Tracer just because. But it creates a redundancy. Every device is connected to every device. It's a lot easier for me to show with switches. So we're gonna use our imagination. All right. So we're gonna have this. So imagine these are computers. I know they're switches. But imagine these are computers. Every single computer is going to be connected to every single computer. So let's get our wiring set up. We're going to be connected like this. We're going to be connected like this. Then we're going to be connected like this. And then this guy over here is going to be connected over here. And then he's going to be connected over here. And then lastly, like that. So this is a mesh topology. And we can set this up, actually. We can set this up to be a real mesh topology. All right. I'm not getting paid by the hour. Maybe I'm entertaining somebody. So let's set it up. All right. So we have our two computers here. Let's link up our computer here to the switch. I don't want that. Go away. And then we'll link you up to the switch. And then we'll link you guys up. That's kind of in essence what we're going for. Here's the example that they use. They just connected every computer to every other computer. So, but this is a mesh topology. All of these switches are connected to every other switch. It's really good in regards to having a lot of redundancy set up. Because if this line gets broken between this switch and this switch, we still have the other lines that work just fine. That's totally okay. Just for fun, because I've never looked at a simulation on this one. Let's do a simulation. We'll set you up as 192.168.1.1. Cool. And then we'll set this one up. Configuration, I'm sorry, desktop IP configuration 192.168.1.2. And let's see how data travels. Let's just check it out. So we'll drop a packet here, and then we'll drop one here. And then let's watch. Uh-oh. Why are we both talking at the same time? Ooh. Yep, we got to learn all of the MAC addresses for all of our interfaces. That's fine. Did we maybe get our packet? Yeah, it looks like we did. We're sending the response. Sending a response. What's happening here? Perfect. Perfect. We're learning things. We're doing the stuff. Hey, looks like we're good. Okay, what's happening now? Is this our original data packet? I'm not sure. And then we should be sending a response. Yeah, I think we had that initial, like we have the burst to where the switches are trying to figure out who is where and what. And this should be our response. We should get our green checkbox. Good. And then we see that we are successful in propagating that. All right, sweet. On to the next one. Yeah, he goes on to explain that you can clearly see that everything gets more and more complex as both the wiring connections multiply. And then he gives us an equation of n times the quantity of n minus 1 divided by 2 connections. This means that the network consisting of only 4 computers, you have 4 times the quantity of 4 minus 1 divided by 2, or 6 connections. Yeah, so 4 times 3, 12 divided by 2 is 6, yep. And if that little network grows to like 10 computers, you can see you have a whopping 45 connections to cope with. So yeah, you have a lot of, redundancy built into this. It's really great in regards to that, but it's going to be a lot more expensive. Just to summarize again, this is the mesh topology. All right, let's move on to the next thing. All right, let me just quickly check the quality of the stream while we're at it. Perfect. Yeah, everything's still going good with the stream, it seems. All right. Yeah, and then if we have any fault or failure in connections, computer can just switch to another network, another connection. All right, so our next one is point-to-point topology. So go ahead and go back to real time. And then we'll just go ahead and delete this. So point-to-point topology. As the name implies, in a point-to-point topology, you have a direct connection between 2 routers or 2 switches, giving you one communication path. The router in a point-to-point topology can be linked by a serial cable, making it a physical network. Or if they're located far apart and connected only via a circuit within a frame relay or multi-point label switching network, it's a logical connection instead. So let's see. So yeah, point-to-point is super simple. Let's get back over to the desktop. Point-to-point is super simple. We either have a PC to a PC, and give me my connections. Fast Ethernet. So we have point-to-point, or we have, let's see, we have router to router. We have point-to-point if we use a serial connection. So that's point-to-point. We have PC to hub as point-to-point, or PC to switch as point-to-point. We can wire these up too. And then wire you up last. Sweet. Those are our point-to-point connections. And one thing he does note is that when we're talking about the serial connections between routers, they show up as a lightning bolt. Like that's just something that they very much so use to illustrate a serial connection between routers. So he says that here, when you see a lightning bolt and a couple of round things with a bunch of arrows projecting from them, right? All those two round things radiating arrows represent our network's two routers. And the lightning bolt represents a WAN link, a wide area network link. So yeah, that's something he goes into detail on. All right, so he goes on to explain that the diagram shows two computers connected by a cable. Yeah, peer-to-peer network, good. I hope you remember the big drawback of peer-to-peer network is sharing. Sharing is not very scalable. With that in mind, you probably won't be all that surprised if both machines have a wireless point-to-point connection. So, yes, that is a point-to-point topology. Point-to-point. So, point-to-multipoint. Yeah, that's an interesting one. So we kind of covered that when we were talking earlier about the campus area networks. But what we'll have with that is we'll take our router, so network devices, and then we'll grab a router. So this will be like this is the example they use in the Network Plus. So we'll have our corporate office, and then we'll have our branch office 1, and then we'll have branch office 2, and then we'll have branch office 3. Yeah, and then we'll go and make it pretty. All right. So he says, again, as the name suggests, we're talking about point-to-multipoint topology. Again, as the name suggests, a point-to-multipoint topology consists of a succession of connections between an interface on one router and multiple destination routers, one point of connection to the multiple points of connection. Each of the routers and every one of their interfaces involved in the point-to-multipoint connection are part of the same network. So we would have the same network. Ooh, can't have a lowercase b there. And we'll get some routers set up for this as well. So there we go, router, and router. Outstanding. So let's go ahead and wire them up. First, we have to go in here and set up some more connections. Let's make sure this is the right one. That's the RJ11. We can't use you. I think this guy is it. LAN applications. That sounds good to me. Let's turn the power off. I keep forgetting to do that. I am sorry. There's so many spots in here to wire stuff. Let's get that power back on. So let's get it. We can use regular cable connection. Fast Ethernet to fast Ethernet. And then we'll go fast Ethernet, fast Ethernet. And then last, fast Ethernet to fast Ethernet. So you can kind of see that, right? It's point to multipoint. So he goes on to explain, like, this is a really good example. And this could be wireless too. This could be satellite. This could be, you know, through the wide area network as well. Let's see. And yeah, your single corporate router would connect multiple branch offices, which we kind of covered in the campus area network, right? All right. Let's see. Am I missing anything? Each of the routers, yep. Perfect. So we're going on to the next thing, and I'll just show you guys for fun the illustration that he has. He has a corporate office and branch offices, and then he shows kind of another illustration of that here. All right, then we have hybrid topology. So he goes on to explain that we just talked about hybrid network topology in the section about mesh topology, but a good mental picture of that was it's a combination of two or more types of physical or logical network topologies working together within the same network. So, yeah, I kind of demoed that when I used the hubs in between the bus topology. So, yeah, he explains that that's kind of essentially speaking what a hybrid topology is. Where he has here in the study guide is he shows that it's a similar type of example that I set up. And this is kind of like a physical star and then a logical bus as well. Like, remember when I had all of the hubs and switches connected across the screen? We can just quickly set up those network devices to show you again. So let's go into our hub, and then we'll grab a switch, and then our hub, and then our switch, right? So we can have our hub, and kind of like a hybrid of this would be, maybe I have a computer here, and then we have a connection to our hub. Why? Boom and boom. So we have our connection here, and then we have, maybe we have some computers that are tied directly into this line, right? So these would be connected directly to this Ethernet line. And then we have the hub connected to the switch, and then maybe we have all of our computers that are separately connected. So that's kind of like the hybrid version that he's talking about. So this would be a better example of the bus topology. Like, we have multiple computers and everything tied into this single Ethernet wire. Everything's tied in. And then we have a hybrid where we have a switch coming over. It's just a mixture of everything. All right. Let's move on to the next thing. Hey, we're almost done. We're 3/4 of the way done. And this is chapter 1. So hopefully once a week I'll try to go and get a chapter of the CompTIA Network Plus study guide done for everybody. All right. So he goes on to explaining here in like one of the fun facts sections that they're just cables, right? Wrong. Regardless of the network, the type of network you build, you need to start thinking about quality at the bottom and work up. Think of it as if you were at an electronics store buying the cables for your home theater system. Like, he goes on to explain, if I recall correctly, like, you've already spent like, I don't know, $1,500 on a projector, and then you spent $800 on your surround sound, right? Are you gonna really cheapo yourself out of cable connections to everything? Like, you've already spent huge money, and cables are actually pretty important. Like, yeah, it's kind of wild, the difference in like the amount and quality of data transmission as you go up through the different types of cables. If you were to compare like Cat 5e versus Cat 8. So like, we'll get into the categories of wires in another video. Or just, like I said, going chapter by chapter with this. But they do cover in depth the types of cables in one of the later chapters, but the quality and then the amount of data that you can transfer with like a Cat 8 is ridiculous, which I have Cat 8 set up in my network. We'll transition over real quick and show you. So yeah, this is a Cat 8, this is Cat 8, and this is Cat 8, this is Cat 6 cabling. And then one of my shorts, I destroyed a Cat 5e cable, which is also a foil twisted pair cable, just shielded, so that way it stops electromagnetic interference. But like, he goes on to say, like, yeah, if you've already spent good money on your equipment, don't cheap out on the cables, because that'll really bottleneck you. Because cables are only rated for a certain amount of bandwidth. Like the more expensive cables, which they were relatively cheap for the Cat 8 cables, But like the better quality you go for, the better you are, because you're future proofing yourself. And then you also want to make sure that you get the most out of what you're doing. All right, so now we're on to setting up the right topology. And we can skip a good amount of that in regards to his breakdown of it, because a lot of it is a matter of figuring out the network that you need to build. Specifically, like what type of network do you need to build? What type of layout are you in? What type of office are you in? How big of a network? Are you setting up a brand new network for a brand new college, or are you just adding new stuff? Like maybe you had an expansion on your house. So that's what he breaks into that. You're looking at things like cost, ease of installation, ease of maintenance, fault tolerance requirement. Like if you're working in a hospital, you definitely want a very robust network, because when you're trying to look at a client's medical history to save their life, you don't want like a busted hub to just ruin your ability to get that info quickly. Um, Security requirements. All right. So then he's talked about the network backbone, which we covered a little bit, right? And I'll show you guys the example he gave for that. Let's switch back over to the desktop. So here's the example he gave. I can't really replicate it in Cisco Packet Tracer, I don't think yet, but we have this backbone, the backbone that goes across the network, and that's a single wire, and things tie into that wire. The wire comes, this wire comes from the backbone and then plugs into the hub. So that's essentially how it differs, in that instead of segmenting it out by having a switch in, well, this is a hub, having a hub in here and then having a switch in here, we're tying off of the backbone and then we're attaching our devices to that. So let's read through what he has to say on that. So there's a standard way of communicating with each other intelligibly about exactly which part of the network we're referencing. So yeah, we divide the different parts into backbones and segments. So yeah, we have our different network segments here. Like we have this segment, we have this segment, and then we have this segment, and lastly our server segment. And then we have our backbone, which carries all the data across everything. All right. And then network segments he references, and it can mean any small section of the network that may be connected to but isn't actually a piece of the backbone. The network's workstations and servers organized into the segments connect to the network backbone. So service-related entry points. He says, in the networking world, there are clearly defined boundaries where only entity hands off a connection, or one entity hands off connection to another. And they're common when you're connecting to a service provider's or carrier's wide area network circuit. So yeah, for example, my modem right here is a good service related entry point, essentially speaking, because that's where my home network hands it off to my internet provider. And we emulated that with having the DSL connection here. So the DSL modem, because from the modem it goes off to the internet. And yeah, we can have our whole network out here. And then when it's here, it goes off to the internet. So that's our service related entry point. So service provider links are internet service providers and cable and telephone companies that provide networking services. There are many different technologies used to provide these features, such as satellite links. Then you have traditional telephone companies that'll use the digital subscriber lines, DSL, digital subscriber lines. So we'll add that to our handy dandy acronym holder. So DSL, digital subscriber Perfect. So far we have LAN, local area network, WAN, wide area network, WLAN, which is wireless local area network, MAN, MAN, metropolitan area network, PAN, PAN, personal area network, CAN, CAN, campus area network, MPLS, multi-protocol label switching, MGRE, which is multi-point generic routing encapsulation, and then DSL, which is digital subscriber lines. And let's see, we'll go ahead and minimize you again. All right. So we have the last little bit to get through. Service provider links. Yeah, let me change mine back up to links, not lines. Service provider links. Service provider links are for internet companies, internet service providers. Internet service providers is another one we can add. That's ISP, Internet Service Provider. Excuse me, had to sneeze there. All right. There's many different technologies for this, such as satellite links for earth station to satellite connections. Traditional telephone companies may have extensive copper connections to homes and businesses that use digital subscriber lines, DSL. Wait a minute. Did they switch it up somewhere? Okay, yeah, digital subscriber lines or DSL to provide last hop high-speed digital services. DSL used to be a popular method to connect to the internet and a solid alternative to copper or fiber connections. So maybe DSL, digital subscriber line, isn't exactly what leads to our ISP or our internet service provider. Maybe that that would be our cable modem, which we have here. So I don't know. Let's take a look-see at it. That's one of the cool things. And like I said, and I'll say many, 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 many times, I'm still learning myself. So let's see if we can zoom in on this. So yeah, it looks like this is going to have our coaxial, and this is our cable modem. Yeah, neat. Let's see if we can set this up for future videos. And what is this? I don't know what this is. I think this is a modem. It looks like a modem almost. But this, actually no, we'll cancel that. All right, sorry, we're going to take a quick aside and see if I can utilize this to emulate the internet. So we have our cable modem, and then let's go and grab a router. Perfect. All right, let's get this connected up. Blackwire, fast Ethernet, and then fast Ethernet to port 1. Or actually, do we do a serial connection? Config, routing. Can we add you? I gotta add an IP address. It's too big. There we go. That's a little bit more user friendly. So let's go and see our settings. So routing, we can set static. I thought this was where we put our IP address. So fast Ethernet 0. We'll set this up to 192.168.1.0. And then 192.168.1.1. And then we get our default subnet mask. That's fine. IP configuration. I'm just doing a quick experiment. Perfect. Oh, we got to turn that interface on. Turn you on, and then interface there. We'll turn you on. All right. Did I get that interface correctly? FA01 or FA00, FA10. Cool. Or do I need to do a serial connection? Let's check this out. Give me a second. We'll go ahead and delete this. Cancel. Let me click the delete button. And can we do you? To you? Hey, I like it. And then we'll set you as the default gateway. IP configuration. Let's see. Default gateway. Oh, we got to configure an IP address for this router. Oh, no, we don't. Default gateway. It's 192.168.1.1. And then we'll set our subnet mask of 255.255.255.0. Oh, I gotta give you an IP address. All right, config. How do I give you an IP address? Let's do this. Config. Are we on serial 20? FA10. FA10 IP configuration IP address 192.168.2.1. Cool. And I don't know that I have to do anything else here. So let's try this. Huh. Yeah, I haven't played with the cable modem too much. I was just kind of curious. I apologize for that distraction. So let's go on. We have our last little bit. All right. So cable companies now offer data and internet services over their hybrid fiber coax networks, in addition to their traditional video offerings. So a cable modem is installed at the customer's site and provides data, video, and voice services off of the cable network. So a beautiful example right here is at my house. I showed you my modem, and we can go back and look at that again. So I showed you my modem. It has coax cable plugged into the back. It plugs into there. It takes the analog it takes the analog electrical signal, turns it into a digital format that my switch and computer can recognize. And then when my computer or other devices at home want to send information back over there, it demodulates it back into electrical signal to go across it. Fiber uses pulses of light. So yeah, those are those two things. Let's see. Another common link is a leased line. When the provider installs the leased line, it is either copper or fiber termination that interconnects two endpoints and is exclusive to the customer. There is no shared bandwidth, and leased lines are very secure as they are dedicated for the customer's use. So, and then he says, as you learned about earlier in this chapter, a metropolitan area network, uses optical fiber. It is sometimes referred to as metro optical network instead of a MAN or metropolitan area network. So yes, I believe, like, as far as I'm aware, like, I have a leased line because it comes directly to my apartment from my internet service provider. But I don't know how that really works out in regards to how it cables to the hookup, because there's like the big boxes outside where the cable hooks up to that switches it and sends it to the ISP, or the internet service provider. So last topic, and then we're done with chapter 1, everybody. We've been at it for a good moment here. So visual networking. So just as the server would have been moving to visualized processes, so has the network world. Is how it is now common to provide networking services without deploying a hardware switch or router. It's all done in software. Companies such as VMware offer virtual switch or vSwitching technologies that provides the Ethernet switched and routing functions on the hypervisor, eliminating the need for external networking hardware. A vSwitch can operate and be configured the same as an external hardware appliance. Just remember, a vSwitch is similar to software virtualization. Virtualized servers do not have a means for inserting a hardware network interface card, since they can only exist in software. A virtual network interface card, or a VNIC, that's something to add to our list. All right, let's switch our color back to black. So we have NIC, which is network interface card, and then lowercase v NIC, go back one more, which is a virtual, or is it virtualized? Let me find you. We have virtual switch, VNIC, virtual network interface card. Network interface card. All right. And then we'll also add in ISP, which is Internet Service Provider. All right. So we have a virtual network interface card is installed to connect the virtual device to the hypervisor, and from there out to the LAN. Network function virtualization. So that's another thing, is NFV, network function virtualization. Perfect. Network function virtualization, NFV, is the process of taking network functions such as routers, switches, firewalls, load balancers, and controllers and virtualizing them. This process allows all of these functions to run on a single device. The magic behind all the virtual networking popularity is the hypervisor. The hypervisor is software that is installed directly on a bare metal server and allows for many virtual machines, or VMs. So VM is virtual machine. So it's basically a computer that's operating inside of software. So a computer in a computer, to make it easier to understand. All right. To run, let's see. Install directly on a bare metal server and allows for many virtual machines, VMs, to run thinking they are using the server's hardware directly. This allows for many servers and virtual network devices to run on a single piece of computing hardware. So essentially speaking, what they're doing is on a single server, all right, we have a single server, they have so much computing power that you can run different operating systems or different computers, virtual machines on their software. Because think about the fact that they have so much data storage capabilities. Like they have tons of hard drives in there and they have a ton of RAM. They have at least 2 CPUs. They can have several GPUs if they need them. Servers don't typically use GPUs as far as I've read so far though. But like you can run different computers inside of that server or you can run different instances of servers doing different things on a singular server. Like you'll need more servers as you get bigger and bigger in your company. But like with a smaller company, I can have one server that runs a plethora of virtual machines on there, like doing different things. And that's what they're kind of saying is like the hypervisor is a type of software that's in charge of running all of those virtual machines inside of the server. And I think we'll get into some more details on virtual machines and servers a little bit later in the study guide. But that wraps up chapter 1. We have a summary, so let's go through the summary. And then they have some questions at the bottom. Let's see if we can get those, all right? And we'll struggle through them, all right? All right, so chapter summary. So solidified your foundation to build your networking knowledge as you go through the book. We learned what a network is. We got introduction to components involved in building a network, like the router, switches, and hubs. Learned about the components required to build a network. Connection methods like peer-to-peer, client-to-server. Also learned about the various types of logical and physical network topologies. We talked a lot about that today, I think. Oh, I did not share my desktop. You guys just saw me writing. Anyway, here's our list that we're at right now. Let's get back over to the summary. See, I am not the best YouTuber. I apologize. I'm just a regular dude trying to help people out and help solidify my knowledge as well. And I'm very good at getting distracted. Furthermore, you learned about the various type of logical and physical network topologies and the features and drawbacks of each. So we learned about the bus method. We learned about star and hub and spoke topology. We learned about the hybrid topology. Let's see. So, and then we wrapped up the chapter with a discussion about network virtualization and equipment, and equipped us with the right questions to ask yourself. You come up with the right network topology for your network needs. Okay, so exam essentials. So here we're getting into the nitty gritty. Know your network topologies. Know the names and descriptions of the topologies. Be aware of the difference between physical networks, what the human sees, and the logical networks, what the equipment sees. And we're going to do an example together. I'm going to ask you. We're going to pause for a little bit, and then we'll see. All right? The second one, know the advantage and disadvantage of topologies. It's important to know what each topology brings to the table. Knowing the various characteristics of each topology comes in handy during troubleshooting. Understand the term LAN and WAN, local area network, wide area network. You need to understand when you would use a LAN and when you would use a WAN. A LAN is used to connect a group of hosts together, and a WAN is used to connect various LANs together. All right. So let's get to this. And I'm going to take a break. Then I'm going to start studying for this week's college. All right. Let's get to it. So we're going to go over our network topologies. I'm going to have a computer. And then what we're going to envision is that this computer is connected to this computer. And then this computer is connected to this computer. All right. So what we're emulating here is that these computers are linked together. This computer is linked to this computer. All right. Actually, I got a better way. Let me get back here. All right. So check it out. Watch my awful drawing skills. So we have this computer is connected to this computer, which is connected to this computer, connected to this computer, and that's connected to that. What type of topology is this? Do you know? All right, this is a ring topology. Let's go back up to it, show you the picture. Perfect. Ring topology. All right. Let's try this. Okay. I think I'm going to have to draw again. So let's get that back up. All right. Let's just create some more room and let's go sideways. That way we can get more area on the screen. All right, you guys ready? Ready for the next one? What type of topology is this? We have a computer. And we're connected here, 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 and here. What type of topology is this? This is our mesh topology. Mesh topology. Here's the picture here. Got it? Sweet. All right. For our last one. Wait, is it the last one? Am I skipping something? Oh no. I don't think I am. I think we're good. No, we got one more after this. We got one more. All right. Here's our next one. Computer. And then we're going to grab the dumb hub. Ethernet. Connect. Why? Perfect. All right, guys, what's this one? Do you know? All right, this is our star topology, also known as the hub and spoke star topology. All right, last one. And we'll get this back up. So we've covered the mesh, the star, the ring. All right, let's get the next one going. I'll use the exact one they did. So we have a computer. And then we have a computer. And we have a server. And we have a computer. And then we have a printer. That looks like a printer, right? And then we have one wire that connects all of this together. You guys know what this one is? This is our bus topology. Bus topology. So normally everything is tied into our, what's this wire called that I'm drawing the dots on? Backbone. Our network backbone. Okay. So that's the different types of topology we have. We have the star, the mesh, the hub and spoke. Also, well, it is the star topology. Yes. I covered it, right? Bus, star, mesh, and ring. All right, let's go back down to the questions. All right. Let's get it. Let's get it. All right. What does this stand for? LAN, LAN. LAN. Local area network. And what about this one? Wide area network. So a LAN connects a lot of local network segments together. A WAN connects a lot of LANs together. Okay? Let's see. All right, we have 10 questions, it looks like. Oh, nope. We have more. So written labs. Can you find the answers to the written labs in Appendix A? What are the 3 basic LAN topologies? Well, we have the mesh, bus, star, ring. There's 4. Am I screwing that up? Right? Right? So we have the bus, ring, mesh, and star. Oh, that's a hybrid. No, no, it's not. I thought there was 4. Let's go back. So, network topologies. Yeah. Mesh topology, that's underneath ring. So we got star. So we got bus, star, ring, and mesh. Why? Why you lie to me? What common WAN topology often results in multiple connections to a single site, leading to a high degree of fault tolerance and has one-to-many connections? Well, that would be point to multi-point, right? Yeah. What is the term for a device that shares its resources with other network devices? A device that shares its resources with other network devices. That would be a server. What network model draws a clear distinction between devices that share their resources and devices that do not? What network model draws a clear distinction between devices that share their network resources and devices that do not? Well, that would be client server, if I recall correctly. What network topology or connection type can be implemented with only 2 endpoints? That would be point to point. What device is generally implemented as a star topology? That would be a hub. What does MPLS stand for? Multi-point labeling service. Let's check our acronyms. Multi-point labeling. multi-point label switching. Multi-point label switching. See, even after I repeated it that many times, all these acronyms are hard. What does WAN stand for? Wide Area Network. Will a computer that shares no resources most likely be connected to the backbone or to a segment? Computer that shares no resources will most likely be connected to the backbone or to the segment. I would say that it's more likely to be connected to the segment because, like, if it's connected to the backbone, that's because a multitude of computers are going to be wanting to access those resources. Let's see. Which LAN topology is characterized by all devices being daisy-chained together with the device at each end being connected to only one other device? That would be a ring topology. All right. So now we have our ABCD questions. We have how many? A lot. Let's work through these. We have 20. Let's work through these. So you need a network that provides centralized authentication for your users. Which of the following logical topologies should you use? Our options are A, VLANs, which are virtual local area networks. B, peer-to-peer. C, client-server. D, mesh. You need a network that provides centralized authentication for your users. Which of the following logical topologies should you use? So, mesh is a physical topology. VLANs, we haven't even discussed, so I think we can get rid of that. And then peer-to-peer doesn't allow us to have centralized authentication, right? That's one computer's hooked to another, one router's hooked to another. So it would be C, client-server, unless I'm mistaken. Client-server makes sense as far as a logical topology because the client, being our computer, talks to a server which stores our user profile data, being our username and our password. And actually, I'm just going to bring this over here. Yeah, we can look at it together. Okay. Number 2, you need a topology that is scalable to use in your network. Which of the following will you install? I don't think bus topology is good because we have to keep tying into the backbone. I don't think ring topology is good because we have to, essentially speaking, unplug a computer, stab another computer in there, and then plug that in, and then plug it into the following computer, which means we're going to have to run tons of cabling. Mesh, horrible, because we have to connect that new computer to every other computer or device. So star topology is the best. So long as we have a hub or a switch that has a lot of open ports. But when we run out of ports, kind of having a problem there. Let's see. 4, right? Oh, no, we're on 3. 3, which of the following physical topologies has the most connections and is the least popular for LANs? Well, most connections we already know is mesh. Off the bat, we know that's mesh. A star topology, everything is just connected to the hub. Ring, everything's daisy chained together. Bus, everything's connected to the backbone. But mesh, every device is connected to every other device. Hey, I feel like we're doing pretty good. All right. In a physical star topology, what happens when a workstation loses its physical connection to another device? So it's just it's a star. It's a hub and spoke, right? Only that workstation loses its ability to communicate is the correct answer. because we're not talking about ring topology. Let's see what C is. The workstation and the devices it's connected to lose communication with the rest of the network. That could be kind of correct, but it's not really how it's set up with a star topology. Everything is connected to the hub. And then D, no devices can communicate because there are now two unterminated network segments. That's not true. So B, only the workstation loses its ability to communicate. Which type of WAN technology uses labels, which enables priority of voice through the network? Well, VPN is virtual private network. That's not really it. Don't know what T1 is yet. LAN just means local area network. Bus is a topology. And then we have multi-point label switching, which is the technology that uses labels and enables priority of voice. It kind of works at that quality of service level. All right. What is the logical grouping of network users and resources called? Ooh, that's good. So we have wide area network, local area network, multi-point label switching, and host. So the logical grouping of network users and resources. That's a weird question. I would say local area network because that's talking about everything connected. And then wide area network is talking about connecting a bunch of local area networks together. Host is just a role that a device is playing. And then multi-point label switching is a protocol that's used for labeling data packets that are traveling for quality of service. So I'm going to go with local area network for that one. Which of the following is a concern when using peer-to-peer networks? A, where to place the server. Well, that's not how that works. B, whose computer is least busy and can act as a server. C, the security associated with such a network. D, having enough peers to support creating a network. Like, yeah, I think D is probably accurate enough because like peer-to-peer is like we're just connected to each other. And like ring topology is kind of ish like that. / mesh is kind of ish like that. Yeah, I'm going to have to go with D, having enough peers to support creating a network, potentially. There's also the issue with the security associated with such a network because there's no server in place to actually go about authenticating users. B doesn't make any logical sense to me. And with A, servers don't really work as peer-to-peer. So I'm going to go with D. Maybe that's wrong. All right, which of the following is an example of when a point-to-multipoint network is called for? When a centralized office needs to communicate with many branch offices, boom. A. When a full mesh of WAN links is in place, no, not really. When multiple offices are daisy-chained to one another in line, that doesn't mean anything. And D, when there are only two nodes in the network to be connected. So yeah, we're going to go with A, which is point to multipoint. All right. Which of the following is an example of a LAN? 10 buildings interconnected by Ethernet connections over fiber optics cabling. Nah, that sounds like metropolitan area network. 10 routers interconnected by frame relay circuits. We haven't talked about that. 2 routers interconnected with a T1 circuit. I haven't really talked about that. A computer connected to another computer so they can share resources. That's a network. Uh, I'm going to go with C, potentially. Two routers interconnected with a T1 circuit. Let's Google what a T1 circuit is. Let's see. Google, what is a T1 circuit? So T1 circuit is a designated high-speed digital transmission line providing a symmetric 1.544 megabits per second bandwidth over copper or fiber optic pairs, developed by Bell Labs in the late 1960s. It carries 24 digitized voice channels or data known for high reliability and guaranteed performance via service level agreements. T1s are used for secure internet access data and voice, particularly in enterprise environments. Let's Google image that. The images don't help me. Yeah, for me, so like 10 routers is a bit too much for a LAN. 2 routers seems about right. 2 routers seems about right. 1 router is even better for like logically associating itself with a LAN, which is a local area network. But yeah, 10 buildings, most definitely not. 10 routers, that's a bit much. Frame relay circuits, 2 routers, that seems about right. Computer connected to another computer so they can share resources. That's a very, very basic definition of a LAN, but could also potentially be the answer. So final answer for me is C, 2 routers interconnected with a T1 circuit. And we can go and check these answers. Where did it say that these answers are? Appendix B. Actually, I got the study guide here. Let's go to Appendix B. Let's see if we're right. Okay. Let me reload the page. I'm probably timed out here because I have to go through my school website to access the CompTIA Network Plus study guide. All right. So we'll look at the answers in a little bit. Let's get through the rest of the questions. Let's see. 9. Yeah, so 9 we said C. Which of the following is a disadvantage of star topology? Well, that would, just off the top of my head without looking at the questions, that would be if the hub dies. So let's see. When a single port on the central concentrating device fails, the entire network loses connectivity. That's wrong. When the central concentrating device experiences a complete failure, all attached devices lose connectivity to the rest of the network. Yes. So B. In a star topology, a more expensive type of host must be used compared to the host used when implementing a physical bus. That makes no sense. It is more difficult to add stations and troubleshoot than with other topologies. That's just untrue. So B. What is the difference between a LAN and a WAN? WANs require a router. So do LANs. WANs cover large geographic areas. Yes. WANs can utilize either private or public data transport. Yes. That's all true. So all of the above. But WANs typically need more than one router. So I don't like how they phrase that, because it connects multiple LANs together. Which of the following provides the most physical layout flexibility in a very large, geographically dispersed enterprise network? Let's see. Bus topology? Absolutely not. LAN switch? Don't think so. Star topology? Absolutely not. Multi-point label switching cloud network? Yeah, 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 I could see that. Yeah, we can scroll up. So multi-point label switching cloud network. It just virtualizes the routing path based upon the label that's issued to the data packet. So what type of network are all computers considered equal and do not share any central authority? That'd be peer-to-peer. So client server? No, the server has authority. C, physical topology? I don't know what type of answer that would be. You'd have to be silly to choose that one. Or D, none of the above? No, it'd be peer-to-peer. Peer-to-peer, no, there's no central authority. What advantage does the client-server architecture have over peer-to-peer? So easier maintenance? Greater organization? Yeah, absolutely. That's where we can centralize all of our files and all that good stuff. Tighter security? Yeah. D, all the above? Yeah, let's go with all the above. Which of the following is an example of a hybrid network? Ethernet switch, ring topology, bus topology, star topology. Well, Ethernet switch, no, that's just a device. Ring topology, absolutely not. Everything's just interconnected to everything, daisy chained. Bus topology, that sounds good. Star topology, well, that's one type of topology. So bus topology seems better because you can take a line off of the backbone and then add a hub and then hub and spoke off that line from the backbone. So yeah, I'd go with bus topology. And we'll see if I'm wrong. Okay. 15. You have a network with multiple LANs and want to keep them separate but still connect them together so they can all get to the internet. Which of the following is the best solution? Use static IP addresses? No. Add more hubs? No. Implement more switches? No. Install a router? There we go. Yep, routers can have different networks talk to each other, as we kind of saw when we first started adding a network segment to another network segment. So yeah, I'm going to go with install a router. So which type of topology has the greatest number of physical connections? That's mesh, just right off the top of the head. So point to multi-point. That's not a physical topology. Star? No. Star, everything's just connected to the hub. Point to point? No. So I'm going to go with D, mesh. What type of topology gives you a direct connection between two routers so that there is one communication path? Let's see. We have point to point. Star? No. Bus? No. And straight? No. So A, point to point. Which network topology is a combination of two or more types of physical or two or more types of logical topologies? That would be hybrid. Point to multi-point is a logical topology, I believe. Bus? No. Wait. Which network topology is a combination of two more types of physical or two or more types of logical? Yeah, bus. No, hybrid. I'm sorry. Getting tired after talking for so long. I apologize. Yeah, I'm going to go hybrid. It's a combination. When designing a network and deciding which type of network topology to use, which items should be considered? Cost, ease of installation, ease of maintenance, fault tolerance. All of the above. Yeah, we want all of that to be considered. All right, so we answered all 20 of our questions. Let's see what the answers are. So You need a network that provides centralized authentication for your users. I went with C, client server, and the answer is C. A client server logical topology allows you to have centralized database of users so that authentication is provided in one place. You need a topology that is scalable to use in your network. Which of the following will you install? I think I went with star topology. The answer is C, star topology. To install a physical topology that provides ease of scalability to use a star network. This is a hub or switch device, and this is the most common LAN network today. Which of the following physical topologies has the most connections and least popular for LANs? I went with mesh 3. D, only a mesh physical topology has point-to-point connections to every device, so it has more connections and is not a popular LAN topology. 4, in a physical star topology, what happens when a workstation loses connection to another device? I went with B. Answer is 4. B. In a star topology, each workstation connects to a hub, switch, or similar central device, but not to other workstations. The benefit is that when connectivity to the central device is lost, the rest of the network lives on. Let me double check, make sure. Okay, yeah, I'm still sharing my screen. Good. Let me get my study guide back up. 5. Which type of WAN technology uses labels, which enables priority of voice through network? I went with C, and 5 is C. Multi-protocol label switching has as many advantages as a LAN protocol. When labels are used, voice can have priority over basic data, for example. 6. What is a logical grouping of network users and resources called? I forget what I actually said for this, but I saw the answer, and it's B, LAN. B is LAN. A logical grouping of hosts is called a LAN, and you typically group them by connecting them to a hub or switch. All right, 7. I haven't read the answer yet, so I'm going to go based on what I think I said. All right. Which of the following is a concern when using peer-to-peer networks? I went with D, right? Yeah, I think I went with D. 7. I was wrong. The answer is C. It is easy to relax about security in peer-to-peer in a peer-to-peer environment. Because of the trouble it takes to standardize authentication, a piecemeal approach involves users' personal preference developments. There is no dedicated servers in a peer-to-peer network, and such a network can be created with as few as 2 computers. Okay, sweet. 8. Which of the following is an example of when a point-to-multipoint network is called for? I went with A. Yeah. Answer is A. When a central office such as headquarters needs to communicate directly with the branch offices, but the branches do not require direct communication with one another, the point-to-multipoint model is applicable. The other scenarios tend to indicate the use of point-to-point links between sites. Okay. 9. Which of the following is an example of a LAN? I went with C, right? Okay, I was wrong. The answer is D. 9 is D, which is a computer connected to another computer so they can share resources. So D, LANs generally have a geographic scope of a single building or smaller. They can range from simple 2 hosts to complex with thousands of hosts. Yep, so 9 is D, as in Delta. 10. Which of the following is a disadvantage of the star topology? I went with what? B? Yes. What's the answer? 10 is B. The only disadvantage mentioned is the fact that there is a single point of failure in the network. However, this topology makes troubleshooting easier. If the entire network fails, you know where to look first. The central device also ensures that the loss of a single port and the addition of new devices to available ports does not disrupt the network for other stations attached to such a device. 11. What is the difference between LAN and WAN? Yeah, I went with all the above, and D is the correct answer. A typical WAN connects two or more remote LANs together using someone else's network, your ISP, and a router. Your local host and router see these networks as remote networks and not as local networks or local resources. Routers use proprietary serial connections for WANs. 12. Which of the following provides the most physical layout flexibility in a very large geographically dispersed enterprise network? I think I went with D, yeah? MPLS Cloud Network? Yeah. 12 is D. Multi-protocol label switching provides logical links between the sites, so branch offices can be easily and quickly added. 13. In which type of network are all computers considered equal and do not share any central authority? I went with A. Yeah. A. In a peer-to-peer network, all computers are considered equal. It is up to the computer that has the resources being requested to perform a security check for access rights to its resources. All right. What advantage does the client-server architecture have over peer-to-peer? I went with all the above on this one. And the answer is all the above. In client networks, requests for resources go to a main server that responds by handling security and directing the client to the resource it wants instead of the request going directly to the machine with the desired resources. 15. Which of the following is an example of a hybrid network? I went with bus. I was wrong. 15 is A. The best answer to this question is an Ethernet switch, which uses a star physical topology with a logical bus topology. All right. Yeah, I was wrong. Whatever. You have a network with multiple LANs and want to keep them separate but still connect them together so they can all get internet. Which of the following is the best solution? I went with D. 16 is D. Routers are used to connect different networks together. 17. Which type of topology has the greatest number of physical connections? I went with mesh. 17 is D. Mesh. The mesh topology, there is a path from each connection to every other one in the network. A mesh topology is used mainly because of the robust fault tolerance it offers. If one connection goes on the blink, computers and other network devices can simply switch to one of the many redundant connections that are up to the running. So 18. What type of topology gives you a direct connection between two routers so that there is one communication path? I went with point-to-point, yeah? 18? A. As its name implies, in a point-to-point topology, you have a direct connection between two routers, giving you one connection path. The routers in a point-to-point topology can either be linked by a serial cable, making it a physical network, or be far away and only connected by a circuit within a frame relay network, making it a logical network. 19. Which network topology is a combination of two or more types of physical or two or more types of logical topologies? I went with hybrid. 19 is B. A hybrid topology is a combination of two or more types of physical or logical network topologies working together within the same network. And then lastly, 20. When designing a network and deciding which type of network topology to use, which items should be considered? Choose all that apply. I chose all of them, and the answer is all of them, A, B, C, and D. Each topology has its own set of pros and cons regarding the implementation, so it's important to ask the right questions and consider cost, ease of installation, maintenance, and fault tolerance. All right, everybody. If you've watched it, thank you. Thank you for being here. I appreciated the comments from you. Chris loves tofu. Thank you for joining. Let me switch over to my camera. Like, it was a long study session. It was very long. How long have we been here? Well, how long have I been here? Let's see. Take a gander at this. Oh. If YouTube wants to cooperate with me. So let's see. Wow. Almost 5 hours. And that's chapter 1. So, like I said, I want to work through it slow and steady. Maybe somebody might find this useful for them. And that's what I'm going for. It also helps to reinforce the knowledge for me. Right now we're in week 5. Chapter 2 is next. Let's see what chapter 2 is about real quick. And then we'll call it here. So chapter 2 is the OSI specifications, the Open Systems Interconnection specifications. So we have the 7 layers of the OSI model, and we'll be working through that. That one's going to be a little rough for me, so please be patient. Like, I'm not a huge expert on it. I remember that we have the application, the presentation, the session layer. So those are like the top 3. And then underneath that, we have transport, network, then data link, and physical. And I think that's 7. 4, 5, 6, 7. Yeah, maybe I got that right. All right, everybody. Thank you so much. I hope you have a good night tonight. Take care, and I'll catch you in the next one. Here's my goodbye video.